Dobrze.
Po czesku tłumaczyli to i znaleźli jakieś czeskie wersje.
Dobrze. A program gdzie mamy? A gdzie mamy program?
Tam na zewnątrz powinno być.
Gdzie mamy program? Muszę sobie Dobrze. Dobrze, a jak się łączymy z Barbarą Kraus? Ona
Na Zoomie.
ale jest już jakoś tam gotowa? Dobrze. Dobrze, no, a to wrzuć już ten swój slajd, co? Czy nie? A nie, bo to jeszcze Krzysiek sam ogłasza, tak? Ty zaczynasz, tak?
Nie.
Krzyśku, czy coś się chcesz ogłaszać stąd? Tak? To nie mikrofon.
A. Musimy chwilkę się wstrzymać, bo jak zwykle. Minutkę można dać. O.
Pół godziny, a mamy takie 25 minut plus 5 minut, tak? Trzymamy się tego, czy?
No, mówię to. Raz wysłałem przez 30 minut, a raz 25.
Ale slot jest 30-minutowy w programie.
30-minutowy.
Czyli 25 plus 5.
Ja im tak dawałem 27 minut i 3 minuty na pytanie.
Ja 25 będę trzymał.
Widziałem, że ktoś się nie wyrabia, to...
jednak jest stosunkowo mało, także w 3 minuty daje się.
Ale do Dragana dużo.
To prawda.
Powinniśmy zacząć.
15 minut. No bo dużo pytań na pewno.
To nie dojdzie do kontrowersyjnych tematów. A nie, on zacznie od
Od razu. Przyłoży.
Można drzwiami trzaskać, jak się wychodzi, czy nie?
Słucham?
Można trzaskać drzwiami, jak się
Można.
wychodzi?
To trzeba... Wczoraj jakieś śpiewy, takie psalmy dobiegały z sali obok, przez moment. Tak. Ale krótko, na samym początku. Nie, mają czyli to jest największa, mają kilka... Tak, ale tamta chyba jest mniejsza. Plus mają kilka takich sal na, nie wiem, 40 osób, 40 krzesełek.
Czy ta jest największa?
To chyba ta jest największa. Na pewno ta jest największa. Okay, so we shall start, and I will start with a short announcement concerning our conference dinner, which is planned today at 7:30. Yesterday evening I have sent you emails. I sent you emails about the location and the time. But I have some practical information that unfortunately there is no many parking places. Fortunately, the Flora Cafe has some places in front of the building, but there's blockade at the entrance. So once you are there, you have to wait a little bit, and then they will remove this blockade barrier. They will raise the barrier. So sorry, and let you in. In case of any problems, you can also find some places at Bagatella Street. Usually there are some, at least in the evening you can find places there. Yes, true. Do not try to park in front of the entrance to Bagatella Street because this is the seat of Prime Minister. And it's not allowed to park there. Okay, that's it. Thanks. The same entrance as the entrance to the botanical garden. So it's open till 7.
Okay, so I think we can start with the scientific session. So welcome everybody. My name is Rafał Demkowicz-Dobrzański, and I have a great pleasure to introduce the first speaker, who is ready. Andrzej Dragan will tell us about his theory of everything. So please, the floor is yours. So 25 minutes plus 5 minutes.
Is it?
Questions.
Okay, thank you very much. Yes, it's a good talk to raise the blood pressure level to everyone. I think it's a wild pleasure to speak live to you. I must admit. It's also a pleasure to speak in front of my former supervisor, just to make him suffer the thought that his educational efforts were all in vain. I'm sure you're all familiar with this figure here. This audience doesn't need introduction. This is a figure from famous Feynman's textbook on quantum theory, and he explains the origins of the quantum theory based on this simple thought experiment with double slit. And he says that there are basically 3 things that you need to know about quantum theory, and everything just follows. Everything else just follows. And those 3 things can be seen in the example of this double slit experiment. The first thing is that fundamental processes are unpredictable, are fundamentally unpredictable. You cannot predict what's going to happen. This is called undeterminism. And this is a fundamental property that was absent in classical physics. Second of all, objects like particles tend to behave like they were in several places at the same time. This is called quantum superposition. I noticed that with age, people tend to be less cautious about these claims, like Aharonov says that electron is in 2 places at the same time period. So I'm not there yet. And third of all, the third thing that Feynman introduces is the rule for computing probabilities of outcomes of certain experiments, and those probabilities are computed using complex numbers associated with every single scenario that could happen to a particle. You have to sum up all the scenarios, take a modulus square, etc. And then Feynman makes the following famous quote. One might still like to ask, how does it work? What is the machinery behind the law? No one has found any machinery behind the law. No one can explain any more of that. You have just explained. No one will give you any deeper representation of the situation. We have no ideas about a more basic mechanism from which these results can be deduced. And the paper I'm going to talk about that we wrote with Arthur essentially can be summarized by saying challenge accepted. So this is the work we published last year. To our surprise, it got quite popular. Last I checked, it had like more than 60,000 downloads. And it's especially awesome because it's essentially a paper about very simple special relativity, classical special relativity. And so it's quite surprising. Arthur doesn't need any introduction in this audience, I guess. And the idea is very simple. So let me just bring you to the chase. So when you derive special relativity, when you teach students special relativity, you can do it in many ways. My favorite one is using the approach that was popularized by late Professor Szymacha. And when he derives Lorentz transformation, he assumes that the transformation has to be linear with some unknown coefficients, a and b. And the purpose of the derivation is to derive the most general form of those coefficients. And you can do it in really few steps. It's very simple. First, you find that there is a relation between b and a, trivial one, and then the non-trivial one is a relation concerning the a coefficient, and it can be shown that this combination of the a coefficient standing here has to be constant. And historically speaking, that constant is called 1 over c squared, 1 of the velocity of light squared, and this way you derive Lorentz transformations. This is the result, and that's one possible solution of that. But it appears that there is another mathematically allowed solution that satisfies all the axioms that we assumed. This branch of solutions is well defined for velocities that are smaller than c, for subluminal observers. But mathematically, there is also another one allowed that involves a slight modification of the formulas. That is highly unorthodox, and it's usually considered to be unphysical. So first of all, you have this other branch of solutions is only well defined for velocities that are larger than c, so it is only valid for superluminal observers, and so it's a kind of completes the first one, so that in general those two transformation formulas correspond to all possible observers, as assumed by Galilean principle of relativity that says that all inertial observers are equally good for descriptions of the physics, and it's widely recognized that this second family of solutions is unphysical because it leads to certain problems with causality, and therefore one normally rejects this other branch of solution by saying that if you would allow it, you would have problems with causality, as I said. But this is not a direct consequence of any of our postulates, because all branches of solution satisfy all the conditions, they satisfy the constancy of the speed of light, etc., etc. It's just they are problematic. So the work that we have written with Arthur is essentially by asking a question: what happens if you treat the other branch of solution seriously? If you make a thought experiment, what would happen if they were allowed? And obviously we are going to run into problems with causality, and that is actually what happens. You do have problems with causality, but to our surprise, it appears that those problems are not really paradoxes, but the consequences of that appear are practically the same thing that we know from the quantum theory. So, as we know, quantum theory is not fully causal, at least not in a classical sense. You can repeat the same experiment twice and get two different outcomes. So the rules of causality in quantum theory are slightly different. And it appears that if you just take those two branches of solution seriously, the quantum mechanical description of reality becomes a straightforward consequence. So the claim of the paper is that you can actually derive those three things that Feynman thought to be underivable from very simple, basic elementary special relativity. So this idea can be summarized by, it's a result of taking seriously two quotes. The first one from Nora Gelman: anything that is not forbidden is compulsory. And the second one from Arthur Eckert: screw your reputation, which we did. And also we can think that Albert Einstein must be rolling in his grave for several reasons. First of all, he hated quantum theory. Second of all, we are saying something about superluminal observer, which is also crazy, but this is not true. Albert Einstein is alive and well. Apparently, he runs a Twitter account, and he tweeted about this result, so it doesn't go so wrong against him. So let me tell you a bit about the basic reasoning, how you can get to the results that Feynman was talking about in his lecture course. So this is the main reason why you don't take into account superluminal observers seriously, or superluminal objects seriously. Consider a very simple space-time diagram where you have two kosher subluminal observers, and they exchange a superluminal signal. Let's consider this scenario. So suppose that there is an event A at which this observer A sends a signal that is superluminal, and it reaches the other guy at B. Now we know from special relativity that there always exists another frame of reference, another subluminal frame of reference, in which the order of these events is reversed. So in this other frame of reference, you have first B, and then you have an A. And then the argument is very simple. If this signal is an information, then in the other frame of reference, the observer on the other side at B would possess the information before it was sent, which is paradoxical, and we cannot have it this way. Therefore, it is usually assumed, we make an extra assumption on top of special relativity, that you get rid of those superluminal objects. It's not a logical consequence of Lorentz transformations or anything in relativity. It's just an extra assumption on top of relativity to get rid of those superluminal observers and phenomena. However, I would like to look at this in slightly more detail. So I think there is we found that something is here overlooked. And let me go back to the first frame of reference. So when I say that a signal is sent, to send a signal, you have to have two things. First of all, you must have some object that carries energy or whatever with a superluminal speed. And second of all, you have to be able to send that object at will. You have to be able to control it, to push the button so that you send the signal or not. This is the way you communicate. You cannot have you must have it under control. So by saying that, I'm saying that there is some mechanism that takes place here before the event A, within that past word line, that has some mechanism that can be controlled, can be triggered so that the particles emitted at the given time, and it's at our disposal. Now, obviously, when we have a mechanism like this that causes the signal to be emitted, the other particle at B is hit with a surprise, so that this event B cannot be predicted in advance by only looking at the past word line before B. Simply because the other observer, the other guy is just an independent guy, he is just sitting there, he's not expecting to be hit by a particle, so there is nothing that would allow this prediction. locally in the word line B. And the same thing has to take place in the other frame of reference. So the question is, to you, what caused the emission of that particle at B in this frame of reference? What is the cause of that emission? So clearly there is no cause here in this word line. You could maybe make a claim that there is a cause of that crazy emission that is far away, possibly in the future at A. But if you are sitting next to B, just here, you will be caught by a surprise. You will see an emitted particle and you will not be able to predict it. That would be completely spontaneous. So locally, there is no deterministic description of that process in this frame of reference, which is one observation. And then you can say that if you want to enforce the Galilean principle of relativity, which is the basis of our reasoning, which says that all frames of reference or inertial frames of reference are equivalent, there can be no preferred frame of reference, then if you notice that there is no local deterministic description of this emission in this frame of reference, then there can be no local deterministic emission in this frame of reference, because that would otherwise select one of the frame of reference, make it preferred. So the only way out here is to either say that superluminal objects are impossible, you have to discard them, which is one way of doing it. But there is also another one, to say that those objects could exist, but they cannot be emitted in a deterministic and local way. They have to be, if they exist, they would have to be emitted in a non-local way or non-deterministically. And therefore, you have those superluminal objects that are emitted spontaneously, and therefore they cannot send information, at least not in an obvious way, because you don't control the source. The source would have to emit those particles unpredictably, and therefore there will be no paradoxes with sending information, because you just don't send any information by having a source that emits something randomly. So this first observation made us think that, well, it's not, at least it's not obvious that this is completely crazy to take into account those superluminal objects. And we just carried on and we wanted to find out what was going to happen if you just take those seriously into account. So the first observation is that if those superluminal objects existed, they would have to be emitted unpredictably, undeterministically. Now, what about normal particles? What about particles that are massive particles? So consider a decay of a massive particle into a pair of other massive particles, like normal subliminal particles. Can this be deterministic, according to the theory? And the usual answer is yes, of course. In classical physics, we have deterministic decay, although it's not so clear, because even if you count the number of degrees of freedom, it's not easy to predict. So you have, if you know the momentum of the particle and its energy here, and you know what are the results of the decay, there is 6 degrees of freedom to be predicted, because there are 6 components of momentum of those two particles, but there are only 4 dynamical equations for the conservation of energy momentum. So special relativity doesn't predict what is going to happen here, but essentially you can still have some sort of deterministic theory here. However, if you do allow the superluminal observers to be part of the description, so if you allow the second branch of solutions that I spoke about, then you can always describe the same process from the perspective of the superluminal observer. And geometrically speaking, a regular Lorentz transformation is just a hyperbolic rotation of space-time, with the axis being tilted slightly with angles less than 45 degrees. The superluminal branch of solutions is essentially the same operation, but with angles larger than 45 degrees. So that essentially flips time and space among each other. And for the extreme case of an observer that is moving with infinite high velocity, the transformation simply corresponds to flipping time and space. So in that superluminal frame of reference, this diagram is simply rotated by 90 degrees and looks like this. And in that other frame of reference, this process looks like a process involving 3 superluminal particles. And you have already shown that when you have a process involving a superluminal particle, it cannot be described with a local and deterministic mode of description. And therefore, in this frame of reference, this process has to be completely spontaneous. And again, if you enforce the Galilean principle of relativity that says everything all frames of reference have to have the same laws of physics, then also in this frame of reference, you cannot have a local deterministic mode of description of this process. So again, if you do allow superluminal observers and objects, one consequence that you have to face is you have to say goodbye to determinism. There is no local deterministic way of describing the process. There is a non-local deterministic theory, perhaps, but there is no local deterministic theory. That's as we have in the Bell's inequalities. But I mean, there is yet not anything clearly wrong with this. At least it's not obvious how this would be wrong. Also, I'm going to talk about the two-dimensional, 1 plus 1 dimensional space-time, which is particularly simple for the description of this, because in 1 plus 1 dimensional space-times, there is a perfect symmetry between those two families of observers, and they will be indistinguishable from each other. So in 1 plus 1 dimensional space-time, you could actually be a superluminal object and not even know about it, because it's being superluminal is simply relative here. Okay, so that's the thing, rule number 1 that Feynman was talking about, undeterminism. What about the ability for the particles to be at several places at the same time? Okay, so consider a simple process in which you have a ray of light, a photon perhaps, emitted at A, bounced at a mirror, and going back to B. And I'm going to say something that is trivial now. If you take two photon detectors, and place them on the path of the photon here, and the second one here, then only one of those detectors can click. If you absorb the photon here and detect it, you will not hear a click here, because there is just one photon. And if you heard a click here, you can be certain that there was no detection before. Now, the same has to take place in all other frames of reference. So let us consider the extreme case of a superluminal frame of reference, the infinitely fast-moving observer, for which the time and space is flipped, and the diagram looks like this. And in this case, the process looks somehow peculiar, because it seems that there is a source of particles that emits two photons, one to the left, one to the right. Because there are two word lines, and none of them is preferred. However, if you take a pair of detectors and place them on those two paths, then you have just found that only one of those detectors can click. If you hear a click here, you are certain that there will be no click here, etc., and vice versa. So it looks like when you don't make an observation, the particle goes along two paths at the same time, but if you do make an observation, you only hear one click. So it's not two particles, it's like one particle at two places at the same time, like Aharonov would say, or is that something that looks like a quantum superposition in the quantum theory. So the second conclusion is, if you do take seriously all that is not forbidden, as Murray-Gell-Mann said, when it's compulsory, then this is a straightforward, trivial consequence that objects cannot be behaving fully deterministically. And second of all, you have to say bye-bye to the rule that every object has just a single path. There will be frames of reference in which object moves along multiple paths at the same time. This is simply inevitable. So that again raises the question, why do you actually assume that superluminal objects are impossible? Well, we have not observed them, obviously, but fundamentally speaking, are they really forbidden? The most interesting discussions appear in the 3 plus 1 dimensional case, but I will try to come to that later. So then you can iterate this whole observation that you have multiple paths. For example, if you already know that you can have a particle move along two paths at the same time, for instance, if you have a particle that is moving along a path and then it's scattered to a state in which it moves along two paths at the same time, then you could always change the frame of reference to the superluminal one and then have a situation in which the particle is moving along three paths at the same time, and you can iterate it, and you can have as many paths as you want. So eventually you end up with many paths taken by the particle. And then the question is, how can you formulate a theory around the situation in which you have a particle moving along multiple paths at the same time? And that's the third point that I would like to show you, namely how to derive the complex numbers and the rule for computing probabilities, which is also a trivial consequence of what I have just said. I have 5 minutes. No, 5 minutes plus 5 post questions, right? Okay, that should be enough. So it goes roughly like this. So we already know that there is no deterministic theory characterizing motion of a particle. You are facing fundamental indeterminism. So the only description you can hope for is probabilistic, and we will try to figure out what is the most general probabilistic description of motion along multiple paths. So there, essentially, we want to find some sort of probability function associated to a diagram like this. And all I want to assume about this probabilistic description is that it's going to be relativistically invariant. I want this to be fully relativistically invariant, which means that if I change the frame of reference, the probability has to be the same. So I know a little bit about invariance in special relativity. For example, proper time along a path, along a single path, is an invariant. This is simple integral, which is proper time along a path is relativistic invariant. And to my surprise, not everybody knows that the proper time is actually this expression up to a constant, which is essentially a integral of energy times dt minus momentum times dx integrated along the path, which is in quantum theory known as a phase of a wave function or something. So this is the same integral if you just substitute those expressions. Yeah, I said up to a constant. Up to a constant. If you multiply it by I 1 over h, and this is going to be the same. So, but this remark actually is very important.
There is no h. The right-hand side has the dimension of the difference is the energy.
Yeah, I mean you have to have a mass. This proportionally constant is mass and over h bar. So that's what is missing. You have to add this multiplicative constant. But up to the multiplicative dimensional constant, this is the same. So, so we will be looking for again. So let me go back. Sorry, we will be looking for a function for describing this diagram that is a function of phases along individual paths. So if you have n different paths, then you are looking for a function, an arbitrary function that is a function of phases along all these individual paths. I'm going to denote this function with a p. So for n different paths, the function has to be a function of n different phases or n different proper times. And I would like the labeling not to play any role in this description, so it doesn't matter which is path number 1, number 2, etc. So I want the function to be completely symmetric. So if you have an arbitrary permutation of indices, it should be the same function. That's assumption number 1. I would like the theory to be time independent, time reversible, so that if I change the direction of time, my function p remains the same, which essentially means that if I flip the sign of all the phases, the function will be exactly the same. And that's kind of obvious assumption number 2. And there is just one more that captures the fact that my functions should be some sort of a probability. So it's a problem to talk about probabilities because in in different theories it has different meanings. In classical theory, probability has different axioms than the quantum theory. You can't add probabilities in the quantum theory. In classical, you can. So it's hard to say what actually probability is. But there is one property of probability that is the same in all possible theories. In classical and quantum, it's this very essential property of probability that is always the same. Namely, if you have two independent probabilistic events that happens with some probabilities, then the probability of the whole is the product of those two probabilities. And this is what we are going to assume here, that if you have a special case of motion in which the particle is going to move along this configuration of paths, where all those paths cross at a single point, then the probability of the whole should be a product of the probability of the first part times the probability of the second part. And since phase is additive along the path, that simply means that the probability of the whole, that involves sums of all possible sums of the paths, should be given by the product of those two probabilities for the first part and the second part. That's all. And what is really surprising is that those simple axioms have very few possible solutions. There's only few solutions. Very, very small number of solutions to this set of assumptions. Essentially, this is a generalized functional Euler equation. Euler had this equation for a single variable. This is a generalization of this. And the special case, special solution satisfying all those axioms is given by the following formula, where you have one number of paths to an arbitrary power. Here you have sum of all the paths with exponential functions with arbitrary constant alpha here. And then you have to multiply by the same thing with the opposite signs. That's the special solution. And the general solution to this problem is a product of special solutions. Now, there is one last step I want to make. This will take me 30 seconds, if you allow, Your Excellency. So, what happens if you have infinitely many paths? If you want to have your expressions valid for the infinite, for the continuous case. Well, in that case, you would have to sum up infinitely many numbers that are greater than 1, which would be also obviously invariant by construction, but it will be an infinite invariant, so it's not a very interesting one. And there's only one way to secure that your expression is finite, even for the infinite number of paths. In that case, that is only possible when the constant that appears here is purely imaginary. Only then you have a chance to add infinitely many numbers, and they will give you something finite. As you know, it's the case for the complex numbers. So you find that the only reasonable or the simplest reasonable description, probabilistic description of a situation in which particle moves along multiple paths at the same time, that has properties of probability is inevitably involving a sum of all possible trajectories with complex numbers associated with each of them. And this is a rule that we know from the textbook of Feynman's. I don't have time to talk about anything else, so the reference for your pleasure. Thank you very much.
Okay, thank you for very inspiring talk. I see Professor Kijowski was first.
I have two comments. First of all, in my opinion, any argument which is based on symmetry between time and length, physical length, is false, and because such a symmetry does not exist in physics, which is already, which is obvious already for my 2-year-old granddaughter, because I have one. Okay, and my second remark, I don't like at all your short introduction to relativity or special relativity, because your formulae which you have written down do not represent any physical reality. Those letters x, t, x prime, t prime are just our mental inventions and represent an extremely conservative way of thinking, because in practice we may use also curvilinear coordinates, and especially what is false, this superluminal Lorentz transformation is not forbidden or rejected. You may perfectly use those t prime, x prime in order to parameterize space-time points, and no paradox is there. However, it has nothing to do with physical reality. This is only a way of thinking about physical reality. Thank you very much.
So, what can you say?
Well, first of all, this is to me, it's a great mystery. What's the difference between time and space? We don't know that essentially. What is the difference? We just experience it. But if you just look at special relativity or general relativity, it's not obvious what's the difference, because the difference is really tiny. I mean, it's just a mathematical sign. It's hard to believe that this is all behind all the differences that we experience. However, if you perform a regular Lorentz transformation, hyperbolic rotation, you have no problem whatsoever to admit that what was time for one observer becomes mixture of time and space for a different observer. Time is mixed up with space. And there is nothing wrong with that. I mean, you know, this is how it works. So what we are doing is not qualitatively different. It's just extending the same thing further. It's not qualitatively different thing. This is an extreme case when you just replace time with space. But with a regular Lorentz transformation, you do it every day by just mixing them up a little bit. And as you know, that time in one frame of reference, that is just time, compared to the time for a different observer for which you have a mixture of time and space as time, those two observers have the same perception of time. So it's not obvious why you would not be able to mix those things. And I understand that your granddaughter has this notion already imprinted in them. So do I, and so all of us do. But we don't really know why time is different from space. It's not obvious from any physical theory that we know. I don't think I fully understood the criticism of the derivation of the Lorentz transformations I briefly introduced. I just mentioned really it.
Okay, maybe let the other questions, and Andrzej will think over it.
There is much more to relativity than just the transformation of coordinates. For example, we have Maxwell equations, we have the Dirac equation. What happens with those equations when you transform them according to your second rule? Are they still invariant? What are the interpretations of the solutions after this transformation?
The answer depends on the dimensionality. That's in short. So that depends on the dimensionality of space-time.
It cannot depend because we know the dimensionality. So what is the transformation property of the electromagnetic field under these transformations?
It has been studied. This is
but this is something that should have been studied at the very beginning, because this is where the relativity really appeared in Maxwell equations.
Yes.
Thank you.
Yes, so obviously the talk is really short. I didn't have time to go into all the details, but this is a problem that has been investigated.
Yeah, so Andrzej doesn't want to answer.
So
another question.
My question is related to the last one. So you're talking about free electrons moving around, but when you couple them to electromagnetism, as far as I can see it, a superluminal observer would see not a free electron moving, it would see a superluminal electron emitting a shower of Cherenkov photons. And so it wouldn't be the same as in the other frame, where it's just moving at a constant velocity and not radiating any photons. So is this a way to test the theory?
Okay, I would say that first of all, you have to impose Galilean principle of relativity, which says that if you have certain phenomenon in one frame of reference, you must have the same phenomenon in all the other frames of reference. So if you have a Cherenkov radiation in one frame, you should expect to have the same radiation, the same kind of radiation in the other frame of reference. Perhaps the interpretation is going to be different, as we have seen what was emission became an absorption in the other frame of reference, but definitely the test would be that whether you can preserve consistency in all frames of reference. And I don't see obvious conflict with that.
I just think of a superluminally moving charge as a set of delta function sources. It's going to radiate.
It's going to radiate.
I think I see where you're going.
Yeah, but that means that the only way to preserve the lack of conflict is to say that when you have this radiating superluminal charge, if you go to its own frame of reference, it also has to radiate. Because special relativity doesn't really decide what is right, what is wrong, what is possible, what is not possible. The only thing that special relativity tells you, in my opinion, is if given a situation in one frame of reference, how this situation transforms for a different observer. It doesn't decide whether the situation is correct or not. So I can consider a situation where I have a sun that is pink and there is a shower of money, which is only believed by certain people with political views. But special relativity doesn't decide whether it's true or not. It's only going to tell you how this situation will look in a different frame of reference. That's all. So that consistency, I think, can be secured here. So as far as I understand, there is no obvious conflict. Obviously, weird situation may appear in frames of reference, but they will be consistent with all other observers, which is the most important and crucial point here.
Okay, I think we have to stop because this discussion will never be exhausted, I guess. So thank you, Andrzej, again for inspiring talk. And now we have pleasure to invite Konrad Banaszek, who will tell us about super resolved imaging, which will be within orthodox framework of quantum mechanics, I guess.
Okay, so while the slides are being set up, let me thank for a chance to give this talk. I should say that I owe the Center for Theoretical Physics one of my very first encounters with quantum optics. This was an internship with Professor Jerzy, which must have been like 30 years ago. I learned about squeezing, I learned about James-Cummings model. Then at the University of Warsaw I learned from Krzysztof Wódkiewicz about Wigner function, and I've been trying to make a living from that knowledge since then, basically. What I would like to tell you is something that is not exactly very quantum, it's rather quantum inspired, because as you will see, most of the idea will belong to classical wave optics, and I should say that there are many people involved. There were many people involved in this line of research. Among them was Rafał Demkowicz-Dobrzański. I'm not sure if this, right now conflicts of interest are very fashionable, so I'm not sure if this constitutes a conflict interest between the chair of a session and the presenter, so I leave it up to you to decide. But seriously speaking, well, this will be about the Rayleigh limit, and the Rayleigh limit is something that is easiest to see. This reminds me of that US Supreme Court justice statement. I know it's pornography when I see it. This was his test. So it's the same story with the Rayleigh limit. I think that not entire screen is shown. There is some. Oh, thank you. So basically, if we image a very simple composite source, let it be just 2 points, then the imaging apparatus introduces some resolution limit, which comes from the spread of a single point in the source plane to the when we detect it in the image plane, and things are kind of okayish when the spread of this point spread function or transfer function is much larger than the separation, but the other way, the separation is much larger than the spread of those individual points, but we run into a problem when the separation is much smaller. We will use in our analysis a very simple Gaussian model of the transfer function, and what this picture implicitly assumes is that we do in the image plane direct imaging. Basically we receive photons emitted from our composite source, and we check for positions, for locations of our composite source. I should say that, of course, this is like a coarse-grained measurement in the image plane. Those individual beams are much larger than the wavelength. We can quantify this problem with the notion of the Fisher information, which is basically the inverse of the variance of the estimator, for example, for the separation between our 2-point sources, which is measured here in the units determined by the spread of the transfer function. And if we ask what is the uncertainty of our estimate of the separation, it scales really badly with the separation itself. When the separation goes to 0, it explodes. We can compensate that by using more and more photons, but it is not exactly very efficient. Let me show you, well, I'm not sure I have to introduce Fisher information in this audience, but I'm very proud of this slide, so let me show it to you. This is a very nice, very general concept, which tells us how much information about a parameter of interest we can extract from a conditional probability distribution of some random variable that that depends on that parameter. So Fisher information deals with so local estimation when the change in this parameter is very small, and it checks for the change of this probability in every bin for every possible value of our random variable. And what matters here is the relative change of this probability for in each bin. It doesn't matter whether this probability goes up or down. What matters is that it should be changing. And then we average over the probability distribution itself, and this way we obtain Fisher information. The operational meaning of the Fisher information is that for any unbiased estimator of the quantity of interest, we are lower bounded by 1/square root of the Fisher information. So now comes the element of quantum inspiration. I believe it came from calculating a quantum analog of Fisher information, which helped these authors realize that this Rayleigh curse is not fundamental. But this led to an idea that can be explained very simply in very simple terms. If we look at what is happening in the image plane, then contributions from our 2-point sources are coherent within those individual contributions. So, I mean, this one blob is coherent on its own, the other blob is coherent on its own. The only incoherent bit is the relation between these two blobs. We assume that our 2 points in the source plane are mutually incoherent, which makes sense. So the idea that comes out from this quantum analysis is that instead of measuring locations of individual photons in the image plane, let us project the signal in the image plane on a certain spatially extent mode. And the form of this mode is very simple. We simply let us take the derivative of the transfer function and let's normalize it. And this normalization factor actually is a very good measure of the spread in the image plane of the transfer function, and we can use it as a unit of length in the image plane. So what happens then? We can, assuming that this separation between our 2-point sources is very small, a small fraction of light will go to this kind of first order mode, or if we want to think about single photons, the probability of detecting a photon in this first order mode will be proportional to the separation squared in our units determined by sigma. But now if we plug this into the definition of the Wigner function, we get very few events that are proportional to the separation squared, but then the derivative of this probability with respect to the changes in the separation is actually quite steep. And when we put those things together, we end up with the result that the Fisher information is finite even for zero separation, which looks quite nice. And this was basically, this idea was called by the authors of this paper spatial mode demultiplexing, and it was a great hit from 5 years ago. But there is a small problem. In direct imaging, we don't really have to align the camera in advance. I mean, if we shift our camera, we just have to relabel pixels of that camera. But here we need to know very well where is the centroid of our system. Assuming that our 2-point sources are equally bright, we should be exactly halfway. What happens if we do not know? For example, if we displace our apparatus and we count photons in another mode. Well, then it can be a very simple calculation shows that this probability we are playing with has a contribution from the source separation, which is nice, and then from the offset of our measurement, which is simply a systematic error. If you have a systematic error, what do you do? I mean, if you have taken a first year course in the basic physics lab, you just measure this probability for different offsets, and then you look for the minimum. The location of the offset tells you exactly where the centroid of the source is, and actually this how far you are from the zero at the centroid will give us the separation. But this may not be the most efficient use of the light coming from our source. Can we do better than that? Well, if you have taken a course in quantum information, you know that a lot of things can be described nicely as qubits, and here is a perfect example of that, because in fact, in this whole story, we have two orthogonal spatial modes in the image plane. The transfer function and its... Great, what have I done? And its derivative. If we have two orthogonal states of a photon here in the spatial domain, we can make a qubit out of them. And now the state of the photons, individual photons coming from our source, can be represented as a block vector. The orientation of this block vector corresponds to the offset with respect to the basis in which we analyze our incoming photons, whereas the shortening of the block vector corresponds to the separation between sources, which makes perfect sense because non-zero separation introduces some mixedness, and the mixedness is reflected in the in this block sphere picture as a shortening of the block vector. So this is what you can do if you have taken the basic quantum information course. But if you have taken an advanced quantum metrology course given by Rafał Demkowicz, then you know that there is a very beautiful generalization of Fisher information called quantum Fisher information. And moreover, you can calculate quantum Fisher information for multiple parameters, which tells you what is the precision of determination of multiple parameters from measurement results that is allowed in quantum mechanics. And it turns out that Fisher information for both parameters can be non-zero, which is very nice. But if we want to determine these two parameters from individual measurements on qubits, from detecting individual photons, we run into problems. And we can see that problem very easily. Suppose that we are somewhere in the vicinity of the north pole of the block vector. If we want to measure the shortening of the block vector, we should use the computational basis. Whereas if we want to measure the offset or the rotation of the block vector, we should use the basis composed of two equatorial states. These things are not compatible. So how come this Fisher information for both parameters looks so nice? What we've got at the bottom is that this quantum Fisher information for multi-parameter estimation assumes collective measurement of multiple probes, of multiple photons, or multiple qubits in our case. So we need to design a collective measurement and a joint measurement. So if you are a quantum optician and you hear about collective measurement, what do you do? Basically, there is one thing you can do, which is Hong-Mandel interference in a right setting. And this is what Michał Parniak with colleagues did a couple of years ago. Basically, he simulated a composite source. He had single photons emitted from one or another point, and then he directed those photons into two input ports of a 50-50 beam splitter, and this makes perfect sense, because one photon serves as a reference to the second photon. If those two photons are in exactly the same spatial mode, in principle, Hong-Mandel interference will be perfect, and we will never see the two photons coming out through different ports. If first photon is emitted by one source, the second photon is emitted by the other point source, this Hong-Mandel interference will not be perfect, and we will see some residual events, one-one events. And those residual one-one events actually carry information about the separation of the composite source, which is great, except that in practice, we will always have some residual distinguishability, for example, in the spectral degree of freedom. So we have to account for that. Moreover, we would like also to measure the centroid. Why not? And the best way to take care of all that is to perform spatially resolved detection in both output ports of the after the 50-50 beam splitter. So that way we obtained Michał obtained two-dimensional maps. He was getting very few photons for those 1-1 events, and a lot of photons, a lot of events for cases when both the photons left through the same output port. But those 1-1 events, spatially resolved 1-1 events, actually carry a lot of information about the source separation. We want to do better than direct imaging. We know that we have to be below the quantum Kramer-Rao bound. If we had perfect visibility in the spectral degree of freedom, we would get this nice non-zero value. But because we had residual visibility, we were starting again from zero for zero separation, but we were able to show that we can go above the direct imaging limit for the visibility that was determined from the experimental results. And actually having the spatial information was critical to beat the direct imaging limit. Without that, it would have been much more difficult. Whereas we basically get estimation of the centroid for free. We are as good as direct imaging can be. Well, of course, this is kind of a proof of principle demonstration. This source was kind of simulated. The question is if we can do better than that. And let me just say that our colleagues, Wojtek Wasilewski, Michał Parniak, work very hard on that in the laboratory. They work on multimode quantum memories that can store a number that can store hundreds of spatial modes. And in principle, this kind of a device could be used to bring this idea of multi-photon interference from a thermal source to practice, except we would need also photon number quantum non-demolition measurement. And we would need also to preserve the spatial mode of those photons measured in a non-demolition way. In principle, one can think about those components as being doable. Another approach, which is kind of brute force approach, is to try to avoid to come up with another solution to this problem of identifying the right spatial mode. If we look what is happening in modern communications based on coherent detection, nobody cares, for example, about mode matching between local oscillator and the field that is measured. We take local oscillator just as a CW wave, and then we synthesize the right mode in digital signal post-processing. Well, in telecommunication, nobody talks about mode matching in coherent detection, that they are simply, they view it as filtering, which makes perfect sense. And this inspired a similar approach to beating the Rayleigh limit using homodyne detection, or more generally, coherent detection. We just perform, well, theoretically, we simulate a spatially resolved homodyne detection, and we try to extract information about source separation in digital post-processing. We can do something like that. Let me just skip details. What is interesting is that in this sub-Rayleigh region, which is here, I slightly changed the measure of the separation. I went from full separation to half separation. So the sub-Rayleigh region is roughly below 1. We observe this sub-Rayleigh feature in the Fisher information. We observe this peak. When the separation goes to 0, Fisher information also goes to 0. The standard direct imaging should go roughly like that, but we get this peak. The more photons, and this peak is more pronounced, the more photons we get. So there is some merit in that. The problem is, which I have to be very honest about, is that we have to receive a lot of photons in the same temporal mode to make this work. So we need bright sources, and this is quite a different regime from the previous case when we were detecting photons one by one. I suspect, and this may be a nice theoretical approach to a nice theoretical project, that this is kind of a collective measurement on a multi-photon Fock states, which might be, and it might be possible to describe it somehow, but I don't have a clear picture how to approach this. So if we have bright sources, we can also perform homodynamic rather than play those tricks with quantum memories. And if I still have a couple of minutes left, even 5 minutes, our colleagues from the quantum optics lab, they actually took this idea and implemented in the temporal domain, which I think is very exciting. What they were able to do using their atomic system is to take incoming light, split the incoming light into two, and apply a time reversal operation on one of the arms. So basically, this can be viewed as sorting the odd component part in the frequency domain and the even frequency part in the and the even part in the frequency domain. Here is S, I think, is the spectral amplitude. So again, this is if we assume that our transfer function is even, this will allow us to sort the transfer function itself from the first order correction, which will be even because it will be given by the derivative. So what they did something quite amazing, because they took this system and they were able to determine the separation between two spectral lines using this interferometer and using standard, well, QMTI stands for quantum memory temporal imaging. They basically, that way they image the time variable, they are able to perform time result intensity measurement, which is the analog of direct imaging. And they were able to reduce substantially the uncertainty of their measurement, which translates also into the analog of Fisher information. What is interesting is that this new technique works for very small separations of the order of tens of kilohertz, which contrasts with recent work by Christine Zilberhorn and collaborators that works for, these are gigahertz, well above gigahertz or terahertz, and they are able to demonstrate super resolution which contrasts with standard approaches. So to summarize, well, the basic idea that we are dealing with here is that spatial coherence in the image plane of imaging systems is a very interesting resource. If we want to use it, we run into a number of problems, and we can try to solve them by either conventional techniques like coherent detection or employ the full apparatus of quantum metrology and try to use the recent advances in experimental quantum information. So let me just finish by wishing CFT happy birthday with that parrot, just to ensure the gender balance. I'm not sure how old Madzia was in that film, but I think she was roughly the. Pardon? I apologize. I'm rude.
Okay, let's thank Konrad for the talk. So we now have time for questions. Yes.
It will be a naive one, so if it's silly, just say it straight away, so I will learn something anyways. So in cosmology, we also, of course, use Fisher information theory, but the biggest problem we actually encounter by trying to draw any conclusion or even trying to understand what is the maximal inference of information we can get, is that this formalism doesn't include any kind of treatment of systematic errors. So I guess how do you approach to this? Because you can have something like different response of your photon detector here function, and that will introduce these systematic errors that are not taken account in the Fisher information theory, and I guess would change the calculation, or this is not relevant at all.
Well, I would say that my first zeroth order approach would be to use quantum Fisher information gets rid of the problem of the detection system at all, which is nice. It deals just with the incoming system. So I calculate quantum Fisher information, then I would assume some kind of a measuring apparatus, ideal measuring apparatus, and calculate classical Fisher information. Then I would see what comes out from the, let's say, simulation of the actual apparatus, and if those things are separated, I would then start scratching my head and trying to figure out what's happening. Well, Rafał is a much better expert in Fisher information than I am.
I would do the same. I
Okay,
mean, basically, hey, maybe this is the different perspective from cosmology or our field. We usually have a setup where we can repeat experiment many times and calibrate our devices, so get rid of systematic errors, and then say, okay, now this is a perfect device with very high precision in terms of, using few resources to have good precision, but systematic errors were somehow removed beforehand, probably usually.
I mean, what I described here is a very simple, a toy version of a problem when we have a systematic error, but we can also determine the systematic error by changing the measuring apparatus.
So any other questions? Yes, please. Mm-hmm.
Thank you for that very inspiring talk. And one transparency, you had a measure of the resolution that was better than the direct imaging when you used the Hong-Umandl effect, and you had 92% visibility, which is probably almost like a perfect coherence between the two.
This was the spectral visibility. Yeah.
Or spectral,
Mm-hmm.
I mean, so that 92% was the visibility of the Hong-Umandl dip, I guess, yes?
Yes, if all the photons were spatially indistinguishable.
Yes, and in this plot you had an error bar as well. And so I was wondering first, what is the meaning of that error bar, and what is the requirement on that visibility to really beat the direct imaging? I mean, there must be a threshold value.
I think the error bar came out mainly from the number of repetitions of the measurement.
Okay.
So this was like an estimate of the variance of an estimate.
Oh, okay.
So then this could have been reduced by repeating the experiment more.
So if you were to reduce that visibility from 92% to a few percent only, let's say, you would still beat the direct imaging if you have enough
No, I don't
photons?
think so.
So there must be a borderline, basically.
Yes, there must be a threshold, and this you can see it. Well, what happens in this story? What happens in this story is that, in principle, if you had perfect visibility, you would be going somewhere to some non-zero value, and then if you have visibility below 100%, that at some point you go to zero. You lose this region around zero separation, and this region becomes larger with decreasing visibility, and this can be approximated by a parabola here. So at some point, this parabola becomes wider than this parabola of direct imaging. What is at the bottom of things is, again, you can do a very simple back of an envelope calculation. What is happening here is that this derivative stays as it was, but you have a constant here. And if you add a constant to this epsilon squared, then when epsilon goes to zero, P in the denominator doesn't go to zero, and this screws things up. Hopefully not our reputation.
Thank you.
Okay, so any other questions? I don't see. So let's thank Konrad again. And the last talk of this session is the online talk. by Barbara Kraus. So, Barbara, do we have you with us? Yes.
Yes, I'm here.
We can see you. Okay.
Can you see the screen?
Yes, we can see the screen. It's not full screen yet.
No.
Okay, now it's full screen. We can see the screen and we can also see you.
Can you see the cursor too?
Yes, the cursor as well. So I think everything is in place. So the Zoom is yours, please.
Okay, thanks a lot. And thanks a lot for the kind invitation. I'm very happy to be here, even if it's just remotely. Just try to move this. Sorry. Okay, so what I would like to talk about are symmetries and entanglement of physically relevant classes of multipartite states. And actually, it feels like I haven't been talking about multipartite entanglement for a long time, but now it feels like we have derived enough results lately so that it probably is interesting for you to listen to this. So when we talk about multipartite entanglement, then I guess that all of us have completely different things in mind. So for instance, some of us might think about applications of multipartite entanglement, so more in the quantum info sense, as we also heard right now, that we use multipartite entanglement to do certain things, like to do one-way quantum computation, secret sharing, metrology, quantum error correction, and things like that. And so this is in the context of quantum information. However, other people might think that, okay, well, multipartite entanglement is important to understand, it's relevant to understand because this is the property that dictates the behavior of our physical system, right? Especially if we are at zero temperature. And so we all have probably different motivations for studying or trying to understand better multipartite entanglement, but I think that many of us would agree that this is an important issue that we want to understand better. On the one hand, to find maybe new applications, or on the other hand, maybe to uncover physical phenomena with that. And this is exactly why I would like to talk about multipartite entanglement. And the outline of this talk will be that I first give a short introduction to entanglement theory. And then we will discuss entanglement and symmetries, which you will see will be somehow strongly related to each other, of generic multipartite states. And generic means really that if you pick a random state, then it's in this generic set. So it's a full measure set in the Hilbert space. Okay, so we will talk about this. I will show you some results for generic states. And this will also motivate the second part of this talk, which is the main part, which is about the entanglement and symmetries of subsets of states. So I will somehow explain that it does make perfect sense to consider not the whole Hilbert space for our states, but to consider actually subsets. And the subsets, I want to choose them to be physically relevant. And by this, I mean that I want to focus on states that are important within certain contexts, like for instance, the stabilizer states, which are relevant in quantum information theory, or matrix product states, which are very important in condensed matter physics, and also permutationally invariant states. So I will then discuss entanglement properties and symmetries of these classes of states. Okay? And what I will focus on throughout the talk are pure states. So I will consider only pure multipartite states. Okay, so let's start and let's briefly go through the definition of entanglement. So entanglement is simply everything that you cannot prepare locally. And this means that you kind of imagine that you have two parties or more parties, Alice and Bob, that are spatially separated from each other, and they have a system. And now they can operate on that system, but they can communicate with each other only classically. Okay, so this is what is called LOCC. So they can act locally, so local operation, and assisted by classical communication. This is what they can do. And as long as your state is generated like that, so that you have Alice has a system, Bob has a system, they operate locally and communicate classically, then the state is separable, so it's not entangled. Okay, so entangled is everything else, everything that you cannot prepare like that, stated mathematically. For pure states, this means everything that cannot be written as this tensor product. Right, now how can we measure entanglement? Well, actually we know, all of us know many entanglement measures, right? So for instance, we have the von Neumann entropy of the reduced states, we have Renyi entropies, we have many others, negativity and so on, and so forth, that we can use to measure entanglement. So that's good, because then you can somehow say that this state is more entangled than another with respect to some measure. And this is the problem, because you would need to always act with respect to some measure, because there are states that, for instance, if psi is more entangled with respect to some entanglement measure than phi, but if you choose another measure, then it's the other way around. Okay? And this is, of course, then if you would say, well, I mean, my state is more entangled than the other, then this is not a valid statement in that case, because if you choose a different measure, then it's the other way around. So it's not more entangled than the other. So this is a little bit unsatisfying, right? That this can happen somehow. It would be perfectly fine if our entanglement measures would be operational. And what I mean by that is that if I would know, for instance, that if this measure is very large, then I can use that state for one-way quantum computation and things like that. Okay, but unfortunately, we have very few measures that are operational. So this is more like mathematically, and then we have this relation, but we know that there can be other measures for which it's the other way around. The good thing is, though, that we are able to sort really the entanglement contained in states with respect to any entanglement measure. And the way this works is via LOCC transformation. So this local operation assisted with classical communication. So what we have is that if we have a pure state psi, which we can transform with this local operation assisted by classical communication to some other pure state phi, then we know for sure that the entanglement of psi is larger or equal to the entanglement of phi. And this is true for any entanglement measure. So this gives us a way of sorting really the entanglement contained in our system. Okay, and the reason for that is very physical. So the reason why this is defined like that is because it means that if I have some application for my state phi, then I can equally well use my state psi for that application, because I can first transform it via LOCC into the state phi. And LOCC is something that Alice, Bob, Charlie, whoever can easily implement. And by easy, I mean that they don't need entanglement for that. Okay, so this is why we say that this is a better resource than this one. Okay, because I can go from this one to that one. So if I need that, then I can do that, but I can also do other things with that, possibly, right? And so the important thing here is really that you can sort entanglement with respect to any. You can sort the state contained in the entanglement contained in the state with respect to any entanglement measure. Okay, so this would then always hold whenever you have an LOCC protocol. And you see already here that I want to make the point that I'm going really deterministically. So I'm transforming psi deterministically to the state phi. It's not that with a certain probability, but really with probability 1, I want to go to the state phi. Okay. So what this means in different words is that actually entanglement theory is a resource theory. And the free operations that we have are LOCC. And the free states are the separable states, so the non-entangled states. Okay, so I want to study now these LOCC transformations. And I want to focus here on single copies of the states that I consider. And as I said, pure states. So let's study this LOCC transformation among pure states with the intent to sort the entanglement. Okay. So to somehow maybe also be able at some point to say, what is the best resource? What is the most entangled state? Okay, and the pictures are all for bipartite systems, but of course they extend to multipartite systems. So LOCC plays here a crucial role, right? Because it's the free operation. So this is what we have to study, this LOCC transformation, because this allows us to sort the entanglement contained in the states. So let me just give you two simple examples of LOCC. So one is just, I do a local unitary operation. So Alice applies some local unitary and Bob applies some local unitary. Of course, they can do that with local operation. And so they transform this state into some other state. And so the entanglement of this state has to be larger or equal to the entanglement of that state. But you can also invert the local unitaries, of course. So you can go backwards, and hence the entanglement contained in these two states is exactly the same. Okay, so this is why whenever we talk about entanglement, we always ignore local unitaries because they do not change the entanglement. And this is the simplest protocol that you could do with LOCC. A more advanced one would be this one. Imagine that I have here my party. So Alice has some party and she applies some measurement to that. And she has, in this case, two measurement outcomes. Depending on her outcome, which she tells to Bob, Bob chooses another measurement. Okay, so this depends now, his choice of measurement depends on Alice's measurement outcome. He performs this measurement and he communicates back to Alice what was his measurement outcome. Then depending on I1 and I2, Alice applies another POVM to her system, and so on and so forth. Okay, so this is a much more sophisticated LOCC protocol, but of course you see everything can be done with local operations assisted by classical communication. So if you manage to go then to some other state, then you know for sure that your initial state was more entangled than the other one. And this is also, in this figure, you also see clearly where the problem of LOCC transformation comes from, because you have to make sure that in each measurement, in each of the rounds that you do, the operations that you apply are complete, so that you have a complete measurement, right? So that you fulfill the completeness relation of your measurement operators. And the other problem is that actually you can show that there are certain instances where you need infinitely many rounds. Okay, so this is why the characterization, the mathematical characterization of LOCC is very, very difficult. On top of that, LOCC is contained in a mathematically much more feasible set of or class of operations, the so-called separable operations, but unfortunately it's really strictly contained. Okay, so this is why the study of LOCC is really something very, very difficult. However, if we want to achieve this partial order in the entanglement contained in our states, then we need to study this LOCC. Okay, because only then we can be sure that our state was more entangled than the other one with respect to any entanglement measure.
Backgrounds. Okay, so this is why I chose these topics, and basically I want to answer this question now, which is, I mean, the chairman already answered, but okay, let me say that what I want to say is I want to ask whether we need complex numbers in quantum theory. Okay, so let's say we all take them for granted because we all take for granted that we need them because you open a textbook in quantum physics and the first postulate you find tells you that to any physical system you associate a complex Hilbert space. Okay, but you may wonder why is it so, and in fact, if you think about it, it might be even weird that you have a theory that it's made of complex numbers to describe physics. Okay, so let's see what we can say about this, and this is a joint work. Okay, I have some problems here with space. But okay, it's a joint work together with these people here. There is Marc-Olivier Renou, who is a postdoc in my group. And then there is Miguel Navasquez, who is a group leader at ICOC Vienna, and people from his group. So this is David Trillo, Miriam Weilemann, Thin. And then there is Armin Tavakoli, who was with Nicolas Gizan, and now he's at ICOC Vienna, and Nicolas Gizan from the University of Geneva. And so I will start by something like very generic. So do we need complex numbers in physics? I mean, complex numbers, they play a very important role in mathematics. I mean, it was somehow hard to accept them at the very, very beginning. I mean, Descartes called them imaginary, okay, as compared to real numbers. And well, if you put this question like this, I mean, do we need complex numbers in physics? Well, you can say like, well, no, okay? Because what is physics? I mean, well, you can say that physics, basically you have stuff going on, like you have particles that have been prepared by devices, and these particles are measured and produce some effects. But at the very end, I mean, here, for instance, I like a lot boxes. So you have, say, a box that prepares particles, okay, and you may have different knobs to put this preparation in different, you have different preparations that you can choose, no? Like pressing buttons or putting a knob in a different position, and this prepares different states, you call them. And then these particles go to different locations, and you make measurements, and you may have different choices of measurements, and you have different number of output, okay? And at the very end, I mean, the experiment gives you describe the experiment by listing the probabilities of observing a given measurement output here and a given measurement output here, and when making a given measurement here, another given measurement here, and preparing a given state here. Okay, so you reproduce this, you repeat the experiment, and you collect the statistics, and this is the description of your experiment. I would say this is what, I mean, physics is an experimental, mostly an experimental discipline, and this is what people do in the labs, right? So they collect statistics, and these are probabilities, real numbers. Okay, we don't need complex numbers for that. So as such, we can say, no, we don't need complex numbers to describe physical experiments, okay? But of course, physics is not about describing an experiment only, but it's mostly about explain them and make predictions about new experiments. And for that, we construct theories. Okay, so theories are ingredients, mathematical objects that we associate to the preparations and the measurements here that explain the statistics we see. Okay, so for instance, if you are in this situation and you believe in quantum theory, you will say, okay, here some quantum states have been prepared. These are quantum states, so say, of two particles, and these two particles are subjected to some measurement here, tensor product, another measurement here, and I will describe this by projectors, or if you want to be more generic, general measurements described by what is called P of M. And you combine these objects with the Born rule. Okay, so if you believe in quantum theory, this is a theory. You provide objects to these devices, and then you give a recipe that explains the probabilities from these objects. Okay, so this is what a physical theory is, and this is what quantum theory does in this particular setup. But you may have other theories, okay, to describe the same statistics. So, and before the advent of quantum physics, all our physical theories were based on real numbers. Okay, so sometimes we were using complex numbers in some physical theories, but they never played a seminal role. It was more to simplify calculation. Okay, so for instance, if you take the electromagnetism, well, we sometimes use complex numbers in electromagnetism, but sometimes because explaining some interference wave phenomena is easier when using complex numbers. Okay, so but I mean, the theory is not phrased in terms of complex numbers. Okay, it's just it's phrased in terms of real quantities, although we use them to simplify the calculations. So then quantum theory came, and then it was the first theory to be formulated in terms of complex numbers, no? Because then if you open a textbook in quantum theory, it will you have this postulate. So when I say quantum theory, I will refer to the standard Hilbert space formulation of quantum theory. Okay, so you open and it says, which is the one formulated in terms of complex numbers. Okay, so it says that to a physical system you associate the complex Hilbert space, then a state of the system is a vector in this space, then a measurement is given by, I'm taking the, say, more orthodox, of course the state can be mixed and the measurements can be P of M, okay, but usually, let's say, to start with, you take measurements that are projective, and then the Born rule tells you how to compute probabilities by computing the overlap. And you know how to compose systems, okay? When you have two systems, you take the tensor product of the Hilbert spaces. And somehow I would say that we take this for granted, and we take for granted. I think almost everyone, at least I was, almost everyone is surprised when sees the postulates of quantum theory. At least I was when I was a student. Okay, but after a while, you get used to them and you accept them. So why is it so? Okay, I mean, and in fact, this is something that worried people. I mean, there is a quote from a letter from Schrödinger to Lorentz, where he says that he doesn't feel, he doesn't like this. He doesn't feel comfortable with this. Okay, and he says like, psi is surely a fundamental real function. Okay, and if you think about it, maybe the only reason why psi is complex is because we know that there is this particle-wave duality in quantum physics. So we are going to describe interference phenomena, and then we do as we did in electromagnetism, and we use complex numbers simply to simplify the notation. Okay, but at the very end, it could be that there is an equally valid explanation in real quantum theory. So this is what my talk is about. I wonder whether this is possible. So what happens if we replace complex numbers by real numbers in quantum theory? And by this I mean the same theory, but I'm just replacing complex by real numbers. Okay, so I take the same theory, by this I mean the same postulates, and I go through the postulates, and wherever I see complex, I put real. So there is only one place where this appears, which is here. So this is what I want to see, whether I can put real instead of complex, and whether I have the same theory or not. Okay, so this is what I'm doing. Yes, so it doesn't play any role in what I'm going to say, okay? But I will have a comment on that, okay? So later I'll talk to you. We will discuss about this. I mean, if you think about it, well, okay, yes. Let me just say. Yeah. So, but here I'm more interested in whether the theory gives the same experimental predictions. Okay, so somehow the Schrödinger equation is just an evolution, but at the very end, experimental predictions are just the probabilities. Okay, so then you will have a state that evolves.
Why don't you just say that these are two component fields?
Very good. We will see. Let me just go on, and you will see. Okay, how things go. Yes. Okay. So this is the question I want to answer. No? Does real quantum theory lead to the same experimental predictions as standard quantum theory? Okay, or can I design an experiment in which I falsify real quantum theory, say in the same way as a Bell test falsifies classical physics? Okay, then I make the experiment, and I know that there is no real explanation in real quantum theory for the experiment I see. Well, I mean, if both theories have the same predictive power, then we may argue that complex numbers are not really essential in quantum theory because, I mean, I can equally live with real numbers, and then I can explain everything with real numbers. It's just a matter of simplifying things. While if then the two theories lead to the different predictions, then complex numbers really play a key role in the theory. Okay, so there are also some important remarks here. Okay, so of course I know and we know that there are real theories that have the same predictive power as quantum theory. Okay, like bomb theory. Well, this is not what I'm posing. Okay, so I'm taking the same theoretical framework defined by the same postulates. I'm just changing complex by real. Okay, so bomb theory is, I would say, a different theoretical framework with the same but I wouldn't say that bomb theory is quantum theory. It's a real non-quantum theory with the same predictive power as quantum theory. Also, I don't find this question, let's say, particularly interesting because by definition they have the same predictive power, so this question is unfalsifiable. Okay, so not really interesting to me. Also, there is an issue with dimension. Okay, so of course I don't expect real and quantum theory to give the same predictions for the same Hilbert space dimension. Okay, because to define a complex number, I need two real numbers. So I can expect that the complex quantum theory will give me a cheaper description of an experiment. And if I try to say, if I have an experiment with qubits, and I try to reproduce this with real qubits, probably I will fail, okay? Because I need more real numbers to describe a complex number. And indeed, there are papers showing that for a fixed dimension, there is a gap between real and complex quantum theory. I would say this is perhaps interesting, but I don't see anything fundamental here. Okay, also because dimension, if you think about it, is not an experimentally testable parameter. It's something that you make an hypothesis or a modelization of your experiment and you fix the dimension, but you are never sure about the dimension of a system. You can never measure dimension. The best you can do is to put a lower bound on dimension. Okay. And in principle, if you think about it, all particles have infinite degrees of freedom that are accessible. Okay, so for me, if you give me a description that requires a complex quantum theory of a given dimension, if I can do it with real quantum theory of a larger dimension, that's fine with me. I don't see anything fundamental there. And for what I'm going to say, it is convenient to adopt the viewpoint of a game, like it happens with Bell's theorem. Okay, so there is a believer of complex quantum theory, and there is a believer of real quantum theory, and then the complex quantum theory has to design a setup for which the real quantum theories cannot provide an explanation. If this happens, then you falsify real quantum theory. So this is what Bell's theorem does, for instance. Okay, so you have a setup making measurements on an entangled state for which the poor classical believer cannot provide an explanation. So I want to do the same here. So this is the problem clear to everyone, because this is fundamental for what I'm going to do. Okay. Okay. Now let's be don't do things. Let's try not to complicate things. Okay. Let's just try to make a particle, no, that it has been produced. Maybe it followed a Hamiltonian evolution, but at the very end, I will make a measurement. Okay. So I will describe things. I mean, you can take pure state, but okay, I will describe with a mixed state, and you make a measurement. I will write this for projector, but it can be a POVM. It doesn't really matter. Okay. So at the very end, you describe your description of the experiment is the statistics you produce. So according to complex quantum theory, you see here, this is what I will try to do. I will try to give a setup in which I make some measurements on a particle, and I have some probabilities. And this is my challenge to the real quantum theory believer. Okay. So explain me these probabilities that I get in this quantum experiment using standard complex quantum theory. Okay, these are complex operators. So now the real quantum theory says, well, this is very easy because I will use the trick that was mentioned before. Okay, I double the dimension, adding an extra qubit. Okay, so this was acting on a given space of dimension d. I double the dimension, I add an extra qubit, and I will use these two states for this extra qubit. Okay, this is states the eigenvalues of sigma y, plus and minus I. Okay, so, there's a typo. Should be a plus minus here. So plus I is with a plus and minus I is with a minus. So what I do, I take the state that the real quantum theorist takes the state that the complex quantum theorist is using in his proposal, and does this trick. Okay, he adds. This is basically what was mentioned before. Okay, so you double the space. So you put this extra qubit in these two states, and you take the complex conjugate. Okay. So now you can see that this state is real, okay? Because if you take the complex conjugate, this is complex conjugate, this goes into minus I, this goes here, okay? You can see that things are permuted. This state is real. And you do the same with the measurement operators, okay? You take the measurement operators here that were complex, you take the complex conjugate, you put I and minus I, and again, these are real. And now you combine them according to the rules of quantum physics. And since probabilities are real, this is equal to this, and you can which is equal to this, and you can see that the trace of these two objects is the same as the trace of these two objects, so you can explain all probabilities, which is what it was said before. Okay, so no matter what you do, I mean, even if you have different states, state preparations, different measurements, I can always explain them playing this trick. So I can, for a system of dimension d, I can always find an explanation in a system of dimension 2d. So there is no way you can design an experiment that I cannot explain with real quantum theory for a single system. Okay, so the real quantum theory is happy. Okay, and the complex is unhappy. Okay, so now sometimes when we present these results, people complain like, oh, but this means that real quantum theory only has access to weird states. No, I'm not saying this. This is just a possible explanation within my theory of your complex, complex theory experiment. I'm not saying that the states in the theory have this form. Okay, they are arbitrary operators. But for me, for the real quantum theories, it's enough to find an explanation of your experiment, even if it's weird. Okay, that's enough. So I'm only saying that playing this trick, I can always explain any experiment in complex quantum theory. Hence, real quantum theory is unfalsifiable in this scenario. And this construction, for instance, you can, and what is happening here is that somehow you are taking the complex and the complex conjugate and you put a label given by this I and minus I that tells you in which situation you are. And for instance, you can also apply a unitary operation and do the same trick. And then you can see that when you apply this real unitary operation on your state rho, the actual state and the complex conjugate follow these two paths that are determined by I and minus I. Okay, so you can also include unitaries in your picture, but I'm not going to do this because I'm only interested in statistics. Okay, so maybe we were a bit too naive, no? I mean, just falsifying this in a single system, we see that it doesn't work. Actually, the proof is relatively simple. Okay, so we know that quantum theory becomes much more interesting when you go to composite systems. So let's try to do what happens with composite systems where we have entanglement, non-locality. Okay, so this might be interesting. Well, the fact that you have non-locality doesn't mean that you need complex quantum theory. For instance, if you take the CHSH Bell inequality, the maximal quantum violation is obtained by real objects. Okay, so having a Bell non-locality doesn't mean that you need complex quantum theory for that. Can we do something to fix this? Because now this is crucial for me. Very good. I should have asked this before. I don't know why I didn't do it. I'm too shy sometimes. So, okay, so here you have the CHSH Bell inequality. Okay, this you can do with real. So what you can do, you take different variants of the CHSH Bell inequality, and this is another Bell inequality. It doesn't really matter. Okay, so it's another Bell inequality that I can construct from CHSH. But what it matters is that we know that a way of getting this maximal quantum violation of this sum of CHSH is by taking the maximal entangled state and making these measurements, and now a complex measurement appears. So this might be a good candidate to falsify real quantum theory. So maybe this works. Okay, we have to use entanglement and non-locality. So this is again the game. So we have a state of two particles. It can be even more, what I'm going to say, but I just represent it for two particles. You make measurements. You have the probabilities. Okay, so this is just a local measurement for Alice, tensor product local measurement for Bob on a quantum state. Can the real quantum theorist find an explanation for that? Yes, he can. Okay, so now before, if you add a single qubit, you don't know where to send the qubit. So what you have to do, you have to send a qubit for each party. In this way, okay? You double each local space. And this is the way you do. So you send I to Alice and Bob, and you send minus I to Alice and Bob, and each local measurement, you play the same trick as before. And when you combine these two things, you get the same probability as before, okay? So the real quantum theorists can find an explanation for any Bell test, no matter how many parties, no matter how you design the Bell inequality, and so on. And you can always do it, okay? And the trick is that you use this correlated flag to synchronize whether you make the original measurement or the complex conjugated measurement. At the very end, these are real operators, okay? So this is just an intuition about it, but if you see it, it's just a real quantum state in which you perform real quantum measurements, local quantum measurements on each party. So the real quantum theory is still happy. Okay, this was proven, for instance, in this paper. I think there might be other proofs, but they did that. Okay, so it seems for years that would seem to be the end of the story. Okay, so recently we found that it's not. Okay, so there is a way for that, and for that you have to use a network. So you have to complicate it a bit. You have to complicate a bit more the scenario, and you have to use independent measurements on each party, but also independent preparations. So if you want, this is a quantum network where you have a complex network made of different state preparations and different measurements. Okay, and these measurements may be even entangled. So you may get two particles and make an entangling measurement on these two particles. And this is what now the complex quantum theory proposes. Okay, and it's like a sort of entanglement swapping experiment. So you prepare the state of two particles, and here you make an entangling measurement, and you have here you look for a Bell violation depending on the measurement results. Okay, so it's possible to design an experiment in which, for all measurement results by Bob, Alice and Charlie violate this CHSH3 Bell inequality I described to you that where there was a sigma y measurement. I'm not going to give the details, there is no time, and I don't think this is the audience where, I'm not sure if everyone here is interested in these mathematical details, okay? But I mean, for all outputs, these two people violate a variant of this Bell inequality that requires complex measurements. So where's the problem with the previous strategy? Okay, and now I'm going to demand that the real guy does the same with putting just replacing these complex operators by real operators. Okay, it's the same game as before. Okay, this I will skip because there is no time for that. Okay. So if we use the previous strategy that worked for a Bell test, we run into a problem because you remember there was this I minus I correlated telling whether to apply the original measurement or the complex conjugate. But now I'm going to check the inequality between Alice and Charlie, and they don't get correlated information. Okay, Alice gets a particle that is correlated to the one that Bob gets, and Charlie gets a particle that's correlated with another one that Bob gets, but Alice and Charlie don't have any correlation arriving to them. You may hope that this swaps the correlations so that they apply the original measurement of the complex conjugate in a correlated way. But, well, you can see that this doesn't work. Okay, so the previous strategy for the Bell test doesn't apply to this case because these two people don't get correlated information to apply either the original measurement or the complex conjugate one, okay? Well, this you have to believe me, but it happens. Okay, does this mean that there is no real quantum theory? No, this means that the previous real strategy doesn't work. You have to prove that there is no real simulation. Okay, so this is just one instance that doesn't work. It was the intuition why we look for this example. But then you have to prove that there is no real explanation in any possible real Hilbert space. Well, this is what we did. Okay, so I cannot tell you, but you have some machinery in quantum information, you use it, and you can prove that there are no real Hilbert spaces and operators, no matter which dimension 2, 3, 4, infinite, whatever. You cannot find real operators here that give the statistics that you get here with complex numbers. Okay, no way. I mean, for details, look at the paper, okay? So this is a... So... yes, so... I mean, of course, the mathematical proof then is a bit... Our intuition was the following, okay? So you understand that this is an entanglement swapping experiment. You have problems to create this correlated flag between Alice and Charlie, okay? Because it has to be created by this entangling measurement. So you understand that the previous real simulation strategy doesn't work, okay? So what we did is we use, in quantum information theory, there is something called self-testing that basically tells you that to get some given violations of Bell inequalities, there is basically one single strategy. So we proved that the correlations you have between these two can be self-tested. So basically, the only possible real simulation strategy is the one with this correlated flag, and since this strategy fails, then there is no other strategy. So we somehow were inspired by self-testing and this swapping of the correlations for the flag, and you put the two things together and you prove it. Okay. But of course, in the team there are very smart people, and then Miguel Navasquez found another way, which is, say, experimentally friendly. See, he found a Bell inequality, standard Bell inequality, and he could compute an upper bound on the violation obtained of this inequality, or the value obtained by this inequality by real quantum theory, and it's smaller than what you can do with complex quantum theory. So in this sense, I mean, this proof is a bit numerically assisted by semi-definite programming, but it's a valid proof. And this is nice because then you can go to the lab, test the Bell inequality. If you get a value larger than this, you falsify real quantum theory in the same way as we falsify local models with Bell inequalities. Okay, so then we put... But this requires 3 parties as well? It's the same setup. So it's the same setup, nothing changes. Okay, it's simply that we had, say, a mathematical proof with this sort of cell testing and things like this. And then we also found this inequality. After that, we found the Bell inequality. Okay, so actually, we posted this paper on the archive. Here is the number, okay? And then, after a while, there was an experimental demonstration, okay? So it was really, I'm not sure with so many papers, there was this 2-month delay between the theory proposal and the experimental paper. Okay, so they made an experiment. Okay, you may argue whether they satisfy all the conditions that are required for the theoretical proposal, but I think it's a proof of principle demonstration of what we were proposing in our theoretical paper. So they were really fast. So this is my last slide. Based on that, quantum theory needs complex numbers to really explain the correlation that you observe in nature. Okay, thank you very much.
Thank you, Tony, for this nice talk. Okay, there are some questions, so maybe we'll start from Professor Kijowski.
Just a minor mathematical remark. Classical mechanics, in classical mechanics, complex numbers appear in a very natural way. In classical mechanics, you have positions and momenta, which are organized into a phase space equipped with a natural symplectic structure, and we are used to mix positions and momenta into complex objects like creation and annihilation. However, a priori, we don't know in which proportion we may add imaginary to real. However, there is a mathematical theorem which tells you that if, moreover, we have to our disposal a Hamiltonian which has certain natural properties, then this proportion is uniquely defined, which means that it implies a unique complex structure on that. Thank you very much.
Yeah, well, I'm not sure if I'm supposed to say... Yeah, okay, I'm not aware of these things because I'm not an expert. Thank you very much. So I think my only point would be that I'm not saying that complex numbers are not useful for physics. For the previous theories before quantum theory, what I'm saying is that I'm not aware of any physical theory that was phrased in terms of complex numbers, although you could use them to make computations. Okay, this is the only...
So what I say is that the complex structure of the classical phase space is given uniquely by physics.
Okay.
Okay, another question here.
As we know, actually, Schrödinger equation can actually can be written in the coupled equation, like you take wave function as a real part and imaginary part. You can make Schrödinger equations completely actually coupled real equation. So like that, actually, whenever you have actually quantum mechanical process, you can always like split like a real part and imaginary part, even operator. So in principle, it's not impossible to actually describe quantum system with a real number, not actually without using only real operator or real state. You can actually have two like different set of actually equation or like process. You can combine together later. You can predict quantum prediction with the real number.
Okay. Yes. Yeah. So again, I don't think Schrödinger equation is. It's very nice what you're saying, and but I don't think it plays any role because here I'm only interested in statistics. Okay, so I can always absorb this unitary evolution into the definition of my state, and the real. I mean, it's like in the Bell test, you never talk about dynamics. You only care about the statistics you get. Okay, but still, I mean, this what you are saying is not in contradiction with what I'm saying. Okay, so if you what I'm saying is the following. Okay, so if you want to describe this quantum experiment. The way we do it in standard quantum theory is by taking this form, where we put tensor products that follow from the geometry of the experiment. Okay, so I have a state here, tensor product another state here, and I have a measurement here, tensor product another measurement here, tensor product another measurement here. And this is the way we compose systems in quantum theory. So I take this for granted. Okay, and then the only thing I do is to replace the operators by real operators. Then this is impossible. Now, if you tell me that you forget about this geometry and you see this as a single system, this is what you are saying, then for sure I can always do with real numbers because a single system can always be explained by real numbers. So maybe I should have said it more clearly during my talk. So I'm buying all the postulates of quantum theory, in particular how I compose systems through the tensor product. So I'm not saying that there is a way of writing these probabilities as a trace of a given state with some given measurements. Just single state and single measurement for all the systems. Of course there is, because for a single system there is always a real explanation. But there is not if you, of course this is what we do in a Bell test, you have local measurements, okay? So I think it's ultra licit and even physical to associate an independent preparation for this state, an independent, because here even I'm still a quantum believer, okay? So in quantum physics, we put a state here, tensor product, another state here, a local measurement here, tensor product, another local measurement here, another local measurement. So I'm taking this for granted. And then there is no real explanation. If you forget about all these details, sure, you can write this as a trace of a real quantum state over a real quantum measurement.
Another question, thank you.
It's clear that that every complex Hilbert space can be realified. So one can do without complex numbers. The problem is with the tensor product. The tensor product of two complex Hilbert spaces. This is we know what it is, but we can also do the tensor product of two real Hilbert spaces, and these two operations. So realification and taking tensor products, they don't commute. If you first take two Hilbert spaces and realify and then take the tensor product, then if I'm not correct, you don't get the same as when you take first the tensor product and then realify.
Yes.
And I think this is the issue.
Yes, I agree with you. So the issue is that tensor product is critical in what I'm saying, because if I don't put a tensor product, I have a single system, okay? But then I would say that it's surprising if you put a tensor product that for a Bell test, even if you have tensor products, you can still make it with real quantum theory. So the fact that you have an issue with tensor product doesn't mean that this automatically guarantees that real quantum theory leads to different experimental predictions than standard complex quantum theory. Because in a Bell test, you have a lot of tensor products appearing for the measurements, and you can still do it with real quantum theory. So what is this telling you is that you have to put tensor products for the measurements and for the states, and then this issue with the tensor product becomes experimentally testable.
Okay, and the last question by Professor Dragan.
So there is an interesting relationship between complex numbers and number of dimensions, and you can see it on the example of spin 1/2 system. So for spin 1/2 system, if you want to have a basis of two-dimensional Hilbert space in z direction, x direction, and y direction, you cannot have three complementary bases with just real numbers, right? We need for two-dimensional space, it would be possible. For three-dimensional, it's not possible. You need complex numbers for that. And therefore, if space was four-dimensional, you would need probably some sort of quaternions to describe four complementary bases of the spin 1/2 particle. So there is also this to consider.
Sure. Well, this is what I was saying. If you fix dimension, then many gaps will appear. But to me, dimension is just a theoretical abstraction. It has nothing experimentally fundamental in a given dimension. I mean, I can simply say, okay, you believe that this particle had dimension 2, but it has 3 or 4. Okay, so I don't see. Yes, but I agree with you. I mean, in fixed dimension, many issues happen.
Okay, it seems that there is another question by Professor Szmariec on Zoom. Can you show it?
Hello, thank you, Tom, for a very nice talk. I have one technical.
Okay.
Yeah, sorry, I couldn't come in person.
I will remember.
I have one technical question. So you said that you assume tensor product when you structure when you have preparations and measurements, right? So, like in standard Bell scenario, there is this issue when you have actually a difference in as far as I remember, like in explanatory power, whether you assume this tensor product structure or just commuting operators, and like what is the scenario? What is the status here in the context of like those network experiments? Like maybe.
So you mean what's the difference between commuting and tensor product? Also with It's a good question. I don't know. Yes, it's a good question. So actually, the value we got for this Bell inequality, we computed with SDP stuff and things like this. So basically, we're working the commuting scenario.
Okay. Thank you.
Okay, and the really last question by Professor Rzeczkowski.
What about quaternions? Do they play any role in your consideration?
No, I don't know. Yes, I don't know. Yeah, sure answer also. I don't know. Yeah, it's very natural. I agree, but yeah.
Okay, thank you for all the questions, and we can move on to the next talk. So the next speaker is Rafał Demkowicz-Dobrzański from the University of Warsaw, and he will tell us about quantum metrology and the true Heisenberg limit in optical interferometry. The stage is yours.
Yes, thank you very much. So I'm really happy to be here, and I also realized that I'm also 41 years old. And I also did my PhD in CFT. No, I will be in November 42. And I did my PhD in CFT, so I'm twice as happy to be here on this anniversary. And today I'll try to tell you about a very simple concept. So the Heisenberg limit is the central concept in quantum metrology, which basically tells us what, in principle, we can do using quantum systems to estimate phase in the interferometer in the simplest setting. So let's start with the simple Mach-Zehnder interferometer and the phase delay phi. And the standard approach to estimate the phase is to send a laser light to one of the input ports. So let's denote it by coherent state, and the other input port we may not even be aware of, so the vacuum goes in. And then we detect number of photons and the output, and actually they will have Poissonian fluctuations when we register number of photons. And now when we try to infer the value of the phase, our estimator will also fluctuate due to this Poissonian statistics, and this results in something called shot noise limit for estimation of the phase. And basically it tells us that the estimation precision with n, when you have the average number of n photons, cannot be larger than 1 over square root of n, and if there are no additional imperfections, we can achieve this limit of phase estimation. Now, in quantum metrology, in theoretical quantum metrology, we usually ask what is the best we can do. So the best we can do here is to replace this coherent state by arbitrary state of light. Let's fix photon number to be our constraint. So arbitrary n photon number in two modes can be written like this, where k n minus k means that we have k photons in one mode and n minus k in the other one. And then also we can have arbitrary measurements. Okay, you can imagine something more general than just photon detection. And then we estimate, and then we ask, okay, now what is the limit on phase estimation? And usually what comes on this right-hand side we will refer to as Heisenberg limit. And when you look for the standard derivation of this Heisenberg limit, it goes more or less like this. In essence, this interferometer is just a unitary channel with parameter phi, okay, which imprints this phase on our state, and then we perform a measurement, and then we have some measurement outcomes with probabilities given by quantum theory. And then the derivation usually refers to the so-called quantum Kramer-Rao inequality, or which involves the concept of Fisher information, because it allows us to give a very general statement abstracting on the particular measurements and estimators we use, because it's valid for any measurements and any locally unbiased estimators. So this bound, this quantum Kramer-Rao inequality, tells us that the uncertainty will never be larger than 1 over square root of quantum Fisher information, and quantum Fisher information for pure states is very easy to compute. You just take the derivative of your state and take the norm, the squared norm of this derivative, and subtract the square of the overlap between the state and its derivative. Okay, for our context, in our context, this unitary that imprints the phase is just given as e to I some generator, a Hermitian generator times phi. And in this case, the Fisher information is especially simple because it's just the variance, 4 times the variance of this generator of this transformation. So this phase imprinting, actually. Yes, the generator that describes phase imprinting. So in our case, it will be just operator representing photon numbers in one arm of the interferometer. Okay, for example, in this upper arm where I put the phase. And then the answer, this inequality looks like this, where this is square root of the variance. So in our case, this lambda is just an operator that has integer eigenvalues from 0 to n, because we use at most n photons. So at most n photons can be in one arm. And then you can try to find a state that maximizes this variance. And it's very easy to show that this is this kind of state, which is an equal superposition of maximum number of photons in one arm and the other. And then you got this inequality. And this is usually referred to as the Heisenberg limit. I have 2 slides after end of my talk. I mean, answering this question, because I expected this question to appear. I mean, obviously you see some connections if you think that phase and photon numbers are somehow conjugate in some sense, but I have a slide which is more precise on it. Why Heisenberg? So please be patient. So now, of course, you have this bound, but then the question is, okay, but is this a saturable limit? So in a sense that if you go to the limit of, I use n photons and which go to infinity, can I have equality here in the end? Okay, so if I use more and more and more photons, can I achieve this bound? And this is by no means clear from this derivation, because this quantum Kramer-Rao bound is a bit, okay, it's a very useful tool, but also very subtle, because it's a local concept. It only looks at the derivatives. And it does not guarantee to us that we can have some operationally meaningful procedure that operates even infinitesimally away from this chosen point if we go indeed to this limit of infinite number of photons, because our precision increases and increases, and we should have some operationally meaningful way to estimate phase without actually assuming that we know it perfectly. So that's a bit tricky, and especially you can see why it's tricky if you, if you think about this nun state, okay, this n0 plus 0 n state, because if you send it through the interferometer, it gives you this relative phase e to I n phi. So obviously any measurement you perform will have this ambiguity, 2 pi over n, yes? You cannot resolve 2 pi over n shifts in phase because the state is the same. So it means that already before the experiment, to make any reasonable experiment with this, you need to know your phase better than this. And 2 pi over n is dangerously close to 1 over n. I mean, it's of the same of the order of magnitude. So you need to know that you need to know the phase already within this Heisenberg regime to say, okay, now I can estimate this within this Heisenberg regime. So this is not clear. I mean, can we really saturate this limit? And somehow it's like assumed implicitly that we can, but I want to argue that you cannot. So actually, to make this picture a bit more general, you can consider a generalization of this interferometer picture by considering somehow a more general unitary parameter imprinting operator, where you have a generator which can have arbitrary levels. Okay, this lambda can have arbitrary levels between some extreme eigenvalues, lambda minus and lambda plus, and additionally you can consider something which is a most general scheme where you use a given unitary gate n times. So this somehow generalizes this scheme where you use n photons in the interferometer, but in the interferometer you simply would say that, okay, I use this n photons. In this picture, they would be like parallel channels. I send each photons prepared maybe in entangled state, and each of them go through the same interferometer, through the same unitary encoding. But here, this scheme is a bit more general because it allows some ancillary systems, controls, and measurements. This is the most general you can think of. So that's why I just show you to tell you that indeed what we derive is fundamental. So there is no way around it. Okay, so we are a bit more general than just the scheme that I described when I was talking about interferometer. Anyway, if you use quantum Fisher information tools, you again derive very similar bound. As I just told you before, the only difference is that we have here this difference between these eigenvalues of this generator. In optical interferometry case, this lambda would correspond to like a generator acting on single photon. So it would have just eigenvalue 1 or 0. So there would be difference would be 1, so that you would have 1 over n as before. Here you would have something more general. So this is usually what is referred to as Heisenberg limit in full generality for arbitrary unitary parameter encoding procedure. Okay, but again the same question remains. Is this bound saturable? So when you trace in detail the derivations of quantum Kramer-Rao bound, you realize that it becomes operationally meaningful in general only in the scenario where we have many repetitions of the experiment. Okay, so like it does not guarantee you really operationally meaningful scenario in a single shot experiment. So if you really want to write equality, you should consider a scenario where you have, for example, n photon interferometric experiment, which you repeat k times, and this k goes to infinity again. And then you can argue that there is a procedure, measurement procedure and estimator that does not require you the knowledge already at the level of 1 over n, but you can reach this precision starting from something further away, okay? And but then there's a price to pay because you use k times as many photons, okay? You don't really use n photons, you use n times k photons. While your Heisenberg limit looks like this, it looks like 1 over n square root of k, because square root is number of k is number of repetitions, and if you repeat experiment, your precision only improves 1 over square root of k, not 1 over k. So actually, this is what I would call poor man's Heisenberg limit, because the true Heisenberg limit, if you use nk photons, should be like this, okay? If you want to really saturate this limit that we talked before, like a fundamental one, where we use all the resources in the optimal way. So the question still is not answered. So the question is, what is the real achievable, asymptotically achievable limit in a single shot scenario if I am given n photons and no more? Okay, but I can do whatever I want with them and go to the limit n to infinity. What precision I can operationally meaningful achieve? I mean, abstracting from any experimental imperfections. Okay. So to really answer this question, you should switch from quantum Fisher information-based considerations to Bayesian approach. Because in Bayesian approach, you can meaningfully state your prior knowledge. So you can say, okay, my prior knowledge is some finite region that my phase is a priori, and then I improve on this. Okay, and I look what I reach in the asymptotic limit. The Bayesian approach, I mean, the scenario is the same, but the difference is here that my cost that I optimize is averaged with some prior distribution, which represents my prior knowledge. And then I again need to minimize this cost over measurements and estimators, so it's very similar as in this formulation before. But in Bayesian approach, you really do not derive the bound, like a Kramer-Rao bound, but you try to really compute this cost, which means that in the end, you will be able to present a particular scheme, like measurements and estimators that achieve this cost. Okay, so this will be the advantage, that we will be able to have a formula which corresponds to some particular measurement scenario, okay? And not only some bound which is not really operationally meaningful. So I would not go into the derivation of this Bayesian cost. I just want to state that when we compute this cost for estimation, we can deal with this most general scheme, with this adaptiveness taken into account, and actually we can prove it for any reasonable prior distribution, because the point is I want to give you asymptotic formula which will be independent of prior, because all the critics of Bayesian approach will tell, okay, but everything depends on the prior. Okay, so fortunately in this analysis I'm only focusing on the limit number of photons going to infinity, so in a sense amount of data rises to infinity, and the form of the prior distribution will be irrelevant provided it's regular enough. Okay, of course we cannot have prior distribution like Dirac deltas and so on, because then we would never get out of this Dirac delta distributions. Okay, so there are some technical issues that the prior should be well approximated by some finite bandwidth distribution, but any reasonable distribution can be done like this. For example, square distribution, like narrow square, can be done like this. You can approximate it like this, and then we derive the asymptotic bound, which is independent of the prior distribution and contains this additional pi factor, okay, in the numerator. And actually, we can also show that this bound is saturable. Okay. So there is a constant factor discrepancy between the Heisenberg limit and what I would call the true Heisenberg limit, so something that is asymptotically achievable. How much time we have left? Ah, great. Okay. Okay, so you may say that this is not a big deal, but I would say that it's at least a very good example why one should be careful with, for example, using quantum Kramer-Rao bounds, I mean, too hastily, okay, without a deeper thinking, and especially when taking like asymptotic limits and considering like single shot scenarios. But interesting things happen when you consider multiple arm interferometry. Okay, so because this was like a single phase to estimate. Now, if you consider multiple arm interferometer, and now you want to estimate all the p phases, which are defined as phases relative to the reference arm. Okay, the top arm is the reference arm, and we have p additional arms. And now let's say our goal is to minimize this cost, which I choose to be this natural cost of square of sum of all variances of all the phases, okay, of these p phases. And now again, the question is, what is the limit on it, and what is the saturable, asymptotically saturable limit? So first, the simplest scenario is to use the single parameter results and think, okay, I will simply perform p experiments estimating each phase optimally, yes? I will split my resources, so my n photons I will split into n divided by p photons and perform optimal experiment estimating a given phase, okay? And then obtain the results. So obviously then I can, if I say that this is like the optimal strategy, which I don't know, okay, but assuming that I restrict to this kind of strategies, I can derive this bound where simply I have p terms here, which will be, all of them will be equal. So I have the square root of p, and then I use this formula pi over n, but replace n with n over p. Okay, because I have so then I have this p to the power 3/2 scaling. So my uncertainty grows like number of parameters to the power 3/2. So actually, when people talk about multi-parameter estimation, they usually think about scaling in terms of number of resources consumed, but also scaling in terms of number of parameters they want to estimate. Okay, so now we have like two different scalings playing together. Okay, so there is this exponent. And now, what we tried to do was to find the optimal joint estimation scheme. So like, now, let's not restrict to this particular scheme where each phase is independent. Try to find a single scheme where we optimize all the phases simultaneously in an optimal way. And again, we did it in this Bayesian framework. Okay? And we derived the following bound. Okay? Again, I will not go into details because they are kind of technical, but the result is very simple. So we get basically almost the same formula, just with some different coefficient. Yes. So here we had pi. Here we have something less than pi. Okay, which is okay because that means we have some improvement. But interestingly, the scaling is the same. So we don't really gain much from this joint phase estimation. And why do I stress this? Because if you go through the literature, you may find like contradictory statements. Okay, and in particular in this paper, which considered the same problem but using quantum Fisher information approach, they showed that this kind of state. Okay, so this is kind of a natural generalization of this nun state, where you have like a nun state in many modes, with some weight corresponding to these modes and some different weight corresponding to photons traveling in reference arm, because somehow reference arm is distinguished in this scenario. So optimally there will be some different weights here and here. And you can use the multi-parameter generalization of quantum Kramer-Rao bound that Konrad was mentioning. And actually, in this scheme, you can argue that it is saturable. I mean, again, it is saturable from some point of view. Okay, from point of view of derivation of Kramer-Rao bound, you can find the measurement for which classical Fisher information equals quantum Fisher information matrix. And you obtain this kind of formula. So the obvious difference is that we have a different scaling with p. Okay. So this becomes more interesting because it's not just a constant factor; it's now different scaling in terms of number of parameters, and actually this is wrong. I mean, you cannot achieve this. It's over optimistic, and the reason why it's not achievable is that you are not taking in these considerations, when you are not taking into account properly this requirement for many repetitions of the experiment to really saturate your bound. Actually, if you did it properly, which is super hard, I don't know how to do it. I just know that it has to be so because we know from Bayesian perspective that there is no operationally meaningful procedure that gives you better scaling. Okay? So I know that if you follow this perspective, to claim saturability, you would need to you would arrive at the conclusion that number of repetitions required to saturate will also scale with p. Okay, and it will give you this additional scaling that would make this two approaches at some point compatible with each other. Yes, I'm finishing. So that was kind of surprising for us. That it's not only constant factor, but you can have different scalings also. Conclusions in terms of scalings that differ depending whether you choose what we would call the operationally meaningful approach using this Bayesian framework, or this a bit simpler but not operationally so well founded in this asymptotic limit and single shot scenario Fisher-based approach. So in this single parameter case, we have this constant factor discrepancy. Here we have this scaling discrepancy. And actually you may, so you should be careful whenever you are dealing with something that scales, that when Fisher information scales better than linearly, and you are really thinking about some saturability issues, you should be careful, because then you cannot use easily the argument of many repetitions, okay, to argue for saturability, and some strange things can happen. Okay, so I will stop here, and then I will move to the answer of the question. So thank you. This is the end of the talk. So maybe I will start with answering the question of Professor
Okay, are there any questions?
So why Heisenberg limit? Yes, I will answer this question first. Okay, so let's look at a problem where I'll try to write an estimation problem where you will see Heisenberg uncertainty relation playing the role. So imagine that you have some quantum state, like standard quantum mechanics course, okay? And we apply this kind of displacement of the state, yes, by position x. So we have operator momentum, and I displace my state by x. So my wave function moves by x. And now I want to estimate this shift. This is the parameter I want to estimate, okay? So actually, in this case, the optimal measurement would be just to measure the position, which is maybe not very surprising. Okay, I know what was the position of this initial state, x0, and now I shift by some unknown position, and I will measure position, and my best estimator will be actually the position I measured. Okay, and the uncertainty actually here of this estimation will be just uncertainty of the distribution of the, I mean, the probability distribution of position distribution probability. So because this state obeys Heisenberg uncertainty relation, I can write this formula. So this is just Heisenberg uncertainty relation, but here this delta p and delta x are given in a slightly different context, because delta p tells me about the property of the state from the point of view of what is the root mean squared deviation with respect to the generator of the shift, so the generator of this parameter encoding procedure, like with this unitary encoding, while delta x corresponds actually to the uncertainty of my estimator, which in this case is coincides with the uncertainty of position operator. Okay, so this is like the simple link, and now further link. If you now look at it in a slightly more general picture, where not necessarily you have you have x and p, but some arbitrary generator lambda, okay, and you shift, you may not necessarily know what to measure, what would be the best measurement to estimate this shift, but actually you may derive some formula which corresponds to what precision you obtain when you measure arbitrary observable A. Okay, this would be the expectation value for some arbitrary observable. And now you use some linear error propagation formula that if I have observable A and I want to infer value of phi, in linear approximation of error propagation, my uncertainty of estimating phi will be just given by something like this. And now I can just compute what is the derivative of A, okay, and I just get the commutator of A and lambda, okay, and then I apply Heisenberg uncertainty relation to A and lambda, okay, and then, as you can see, I obtain this formula, and in the end I plug in this relation, and I get this relation, which is exactly the same I got from this Kramer-Rao inequality. Okay, so I hope this now.
Okay, other questions?
I have a very quick question. When I saw your first slide, I thought this was going to be a talk about LIGO.
No, I have a different...
if I was trying to design the next generation LIGO, is there anything in your work that would help me increase the signal to noise?
No, I have different talks. I have different talks on this, but because I gave them so many times, so today I gave something different. This is like, I would say, fundamental talk about some idealized scenarios because there is no decoherence and loss. Actually, but this is also a relevant question because when you take into account decoherence and loss, typically, you also can show some quantum gains, but they will not be in terms of better scaling. So you will not have Heisenberg scaling anymore. You will have this shot noise scaling with some coefficient which is better than if you just use coherent light. And actually, these schemes, you can show that what they do in LIGO actually is optimal in terms of fundamental theory. You can show that using squeezed light, squeezed vacuum light and coherent light with this technical regime they are operating is actually optimal from the fundamental perspective that I describe here. But in relation to this talk, it's also important to mention that in this case, there will be no discrepancy between Bayesian and Fisher approaches because the scaling is like shot noise scaling with some coefficient, different coefficient, but it doesn't matter. It means that always when you think about a single shot experiment with many, many photons, you can think that, okay, I divide it into some subgroups of photons which are large enough so that my precision is epsilon close to the optimal precision, and I can write an equivalent model with many repetitions, and that's why all the quantum Fisher information machinery is guaranteed to lead me to like saturable limits. And Bayesian will give me the same. So then there is no advantage of this Bayesian approach. So the advantage of Bayesian approach is only in single shot scenarios where you have better than classical scaling of precision. I mean, from the operational point of view.
Other questions? So maybe I would have one. So you presented this formula for the single phase estimation, this like most general Heisenberg limit that depends on the eigenvalues of the generator.
Yes.
So why the same formula for many phases doesn't depend on the eigenvalues? So
okay, no. Sorry. For many phases, I assume the standard interferometry without this lambdas.
Can it be generalized?
Maybe, I don't know. I don't know. We didn't do it. No.
Maybe it's worth doing it, no? Okay, let's thank Rafał again for the nice talk. Maybe first I will introduce you, okay? So the next speaker is Dariusz Chruściński from the University of Toruń, and he will give a talk entitled Universal Constraint for Relation Rates for Quantum Dynamical Semigroup.
Okay,
Tough title.
Thank you, Remik. I'm very honored to be here to take part in this conference. So my first visit to Center for Theoretical Physics was exactly 35 years ago. I was a student at that time at Nicolaus Copernicus University, and I remember once Professor Jerzy Duszyński came to Toruń and gave very interesting and refreshing talk on symplectic relations in physics. I was very, very interested in that talk, and after the talk I started to ask questions, talk to him, and at some point he invited me to visit him at the center. So I remember at the time I studied his book with Tulchiev on symplectic framework for field theories, and after some time I visited him. I remember the center was located in a very, very small building, perfectly hidden from the environment. And already at that time I met Maciek, who told me that I'm in very good hands, yes, working with Jurek. So under Jurek supervision, I did my master and then a PhD. Only after that I met Marek and Karol Rzeczkowski, with whom I have now very nice collaboration. Okay, I did also some work on Born-inferred and nonlinear electrodynamics in the 90s, and I remember very valuable comments from Professor Białnicki. I had with him very interesting discussion on Born-inferred nonlinear electrodynamics. But today I will talk about slightly different topic, namely quantum dynamical semigroup, if techniques allows to do this.
So unfortunately, there are some technical problems with the presentation, and we have to wait for Krzysiek. He went somewhere, so there will be a small delay. Okay.
So I wanted to avoid possible problems with my computers. That's why I sent this morning the presentation to the organizers.
I mean, in the greenhouses of Botany Garden, which was grounded in 1918, which are close to the restaurant that we are going tonight. There used to be, unfortunately died, the so-called biggest flower of the world, or of Earth, okay, which has a strange name, Astraphallus titanus or something, because the shape is a kind of 3 meter long ellipsoid cigar shape. But unfortunately it died. It is very rare plant, which is only in few was in few botanical gardens in the world. And now there you can only see the place where it was, but still.
So today we have a chance to see the place, not the flower.
Because the botanical garden is closed at 6.
Ah, okay.
Today, then you should go before 6, it's worth. Okay, should I continue?
You can start, yes.
Okay, so this is a joint work with Gen Kimura from Shibuya Institute of Technology. So let me start with a very basic notion of a quantum channel. What I mean by that, I will skip sophisticated mathematics, and I will consider only finite dimensional Hilbert space in my talk, and by B of H I understand just operators acting on H. So by a map which is by a linear map which is completely positive, I mean a map which can be represented in this form. Usually we call it Kraus representation. These K operators are so-called Kraus operators, and this map is also trace preserving if the Kraus operators satisfy this additional property. For example, unitary map is a perfect example of a map which is completely positive and trace preserving. So you see quantum channels which are completely positive and trace preserving maps provide huge generalization of unitary maps, which we know from standard quantum mechanics. Now let me consider a family of such maps parameterized by time, which is non-negative, right? Such that initially this is just identity map and satisfies this standard composition law, which defines a semigroup, right? So as we know, any such map can be fully characterized by the corresponding generator, yes, the script L, and the question is, what are the properties of the generator such that the map defined by this formula is completely positive and trace preserving? And this problem was solved more than 40 years ago by this gentleman, and they found necessary and sufficient condition for the generator, which is displayed here. So the generator L generates a family of completely positive and trace preserving maps, dynamical semigroup, if and only if it can be represented in this form, where apart from the standard, Hamiltonian part, there's an extra piece which we usually call dissipative part, and this piece, this dissipative part, has universal structure, where this capital L operators are completely arbitrary, right? From the mathematical point of view, they are completely arbitrary. The only constraint is that these real rates, gamma k, are positive, right? So this is a universal form of the generator of completely positive and trace preserving semigroup. Unfortunately, one of the founders of this result, Andrzej passed away this February. So Andrzej Kosakowski,
passed away this February. So I dedicate this talk to his memory. So once again, this is a general representation, right? It should be stressed that this representation is not unique. So we can find another family of L operators and gamma rays, giving rise to the same dissipative part. Moreover, even the splitting into the Hamiltonian part and dissipative part is not unique. That's why, as you see, these rays are rather mathematical objects. For sure, they are not directly measured in the experiment, right? So my question, the problem we are considering, or the problem we are posing, is to find some physical properties, kind of physical manifestation of complete positivity, which is encoded into this very structure of the generator, right? And actually, this physical properties of physical manifestation is fully encoded in the spectrum of this operator, which, as you know, does not depend on the representation. So what we know about the spectrum? Because the generator by the construction preserves hermiticity, so for sure it's symmetric with respect to real line. There is a leading eigenvalue, which is 0, and the corresponding eigenvector, after appropriate normalization, defines a legitimate density operator. And the remaining eigenvalues satisfy this condition. So using this property, well, otherwise the evolution is not well defined. For example, for qubits, you immediately leave the block ball. So using eigenvalues, which enjoy this property, usually people define relaxation rates or equivalently relaxation times, and these are objects which can be measured in the laboratory, right? So once again, these mathematical objects control complete positivity of the corresponding evolution. On the other hand, we have a real part of the spectrum, which defines the relaxation rates. And of course, the necessary condition for relaxation rates is that they are positive. However, positivity of relaxation rates is not sufficient for complete positivity of the evolution. So let me give you an example which was already considered in the seminal paper by Gorini, Kosakowski, and Sudarshan. This is, well, one of the prominent examples of the qubit dissipative dynamics. Apart from this standard Hamiltonian part, we have three well-known operators, especially in quantum optics. This is responsible for the pumping, this one for the damping, and this describes just qubit decoherence. So it's very easy to compute the corresponding relaxation rates. These are given here. So basically, because of the axial symmetry, there are two rates, so-called transversal one and longitudinal one. And actually, it's very easy to check that the following well-known condition is satisfied for the relaxation times corresponding to this generator. So actually, if this condition is violated, the evolution cannot be completely positive, right? And actually, this condition was already well tested in the experiment. So very often one uses the corresponding Bloch equation or Bloch representation for the qubit evolution. So this is just this Bloch representation. And actually, to stay within a Bloch ball, it is sufficient that relaxation times are positive. However, to be sure that the evolution is not only positive, but also completely positive, this much stronger condition has to be satisfied. So this is an example of a physical condition between the relaxation times, which is necessary to have evolution which is completely positive. Not only positive, but completely positive. Okay, so the same example. Observe that if I define a total rate, just summing all three rates, then I immediately arrive at the following constraint for each single rate. That any single rate, gamma k, is upper bounded by half of the total rate. And actually this is not an accident, because it was proved almost 20 years ago by Gen Kimura that this result is satisfied for any qubit Lindblad generator, right? So if you take a total rate, any single rate is upper bounded by half of the total rate. Well, in terms of well, you can define this relative rates, capital RK. So relative rates, all relative rate is upper bounded by 1/2. And actually, this result was slightly generalized by Wolf and Sirac in 2008. They proved the following result, that operator norm of the purely dissipative generator is upper bounded by 2 gamma over d. So out of this you can immediately find the following constraint for each single relaxation rate, that it is upper bounded by 2 gamma over d. And few years ago, Gen Kimura found a tighter constraint. He found that any single relaxation rate for completely arbitrary Lindbladian can be upper bounded by square root of 2 over d times total rate gamma. And our question was, is it possible to still improve the bound, to find a tighter constraint, which possibly can depend on the dimension? And actually it is possible. And in this recent paper with Japanese colleagues, we showed that the optimal constraint, CD, satisfies these bounds, right? So as you see, if D is 2, we recover Kimura result just 1 over 2. But if D is larger than 2, we get tighter constraints that Kimura got a few years ago. It's strictly less than square root over 2. I'm not going to present a proof which is very technical and rather boring. Instead of this, I would like to convince you that the proper constraint is just universal, does not depend on D, and equals 1. So we pose the following conjecture, that for arbitrary Gorini-Kosakowski-Sudarshan-Lindblad generator, any single relaxation rate satisfies this universal constraint. So once again, I take arbitrary generator, compute d squared minus 1 rates, define a total rate gamma, and we conjecture that this condition is satisfied, right? So we were not able to prove it, so we started with some numerical test. So this is numerical test. We just built up random Lindbladians in these particular dimensions and observed that, well, for D, if D equals 2, the conjecture is true because it was proved 20 years ago. This blue vertical line is the previous result, square root of 2, right? And our conjecture expects that this cloud of eigenvalues lies to the right of the red line, right? And actually, recently with Karol Rzeczkowski and collaborators, we studied a similar problem. I mean the spectra of random Lindblad operators, in particular what happens to the spectrum in the limit of large dimension. And interestingly, we found that here n is d from previous slides. We found a very universal result, which is displayed in this plot, that if we renormalized by the dimension, well, we shift by 1 and renormalize by the dimension. After this trivial operation, we find just universal structure. Because of the shape, we call it lemon-like structure. Actually, the structure does not depend on a way you generate random Lindbladians, right? But let me come back to our conjecture. So again, we conjecture this result, and actually we were able to show that the constraint is tight, cannot be improved. It's true for unital semigroups. It's true for so-called covariant semigroups. I will show what does it mean by that. And most importantly, it is true for a very important family of generators, so-called Davis generators, which emerge in so-called weak coupling limit, which is well known, for example, in quantum optics. In quantum optics, these are basically generators which are defined when you apply this well-known rotating wave approximation. Moreover, if this conjecture is true, it has very, very interesting implications. Some more details you can find in this recent paper with Gen Kimura. Actually, it was very last paper of Andrzej Kozakowski. So, as you know, there are two equivalent pictures of quantum dynamical description. So the generator I already showed you, this is a generator in the Schrödinger picture. But of course, you may define the corresponding generator in the Heisenberg picture as well. So this is a definition, right? So you see they are very, very similar. And now using these two equivalent pictures, it is well known that the spectra of Schrödinger and Heisenberg picture generator are essentially the same. Moreover, for Schrödinger picture generator, you can always find equilibrium state, right? And similarly, for the Heisenberg picture generator, it is well known that it kills identity operator. Actually, this condition is, well, equivalent to trace preservation of the original, of the dynamical semigroup. Okay, so starting from the basic structure of the generator, and assuming that the equilibrium state is strictly positive definite, one can introduce the following inner product in the space of operators and the corresponding norm defined in terms of this inner product. And finally, one can find the following relation for the relaxation rates, right? So these are defined in terms of Heisenberg eigenvectors. Well, eigenvectors in the Heisenberg picture. This Y alpha, right? And this formula uses this norm defined in terms of the equilibrium state. Now the point is that if we use this universal formula for the rates and assume that the equilibrium state is maximally mixed, which means that the semigroup is unital, so the Schrödinger picture generator kills identity. This norm defined in terms of equilibrium state, just in this case is nothing but the norm defined with respect to standard Hilbert-Schmidt inner product. So in this case, this formula reduces to that one, right? And finally, using this very intricate inequality, which was proved more than 10 years ago by these guys. So this universal formula for relaxation rates plus this inequality eventually gives this bound for any separate relaxation rate. So this result was very promising. So the next example of generators we studied, these are generators which are covariant with respect to unitary operators defined here. So this is just the maximal commutative subgroup of unitary group in D dimensions. And also, mainly because of the high symmetry of the problem, we were able to prove that this constraint is satisfied. And finally, we consider the family of Davis generators. As I said, these are generators which you can derive starting from the proper physical microscopic model of a system interacting with environment and providing some sophisticated family of approximations. Eventually, you derive a generator which possess very nice properties that if you find the equilibrium state, this is a spectral representation of an equilibrium state. So the Hamiltonian is diagonal in the same basis as the equilibrium state. Moreover, the dissipative part of the generator in the Heisenberg picture is Hermitian with respect to this interesting inner product defined with respect to equilibrium state of this generator. And also for this family of generators, we were able to prove that this constraint is satisfied, right? So we have a nice numerical confirmation of the conjecture. Moreover, several important families of generators considered in the literature already, especially this family, satisfy this conjecture. What are possible implications? Let me mention two of them. One is related to the spectra of quantum channels, and the second one is related to the important question. Suppose you are given a quantum channel phi, and you ask whether is it possible to represent the channel as an exponential of the Lindbladian, right? Very often this problem is, very often people call it Markovian channel, right? Okay. So look, if I take suppose that phi is arbitrary channel, then if I subtract identity channel, this defines legitimate Lindbladian. So if I know this constraint for the Lindbladian, I immediately get the corresponding constraint for the channel. And it's very easy exercise that if you find the spectrum, this is a spectrum of suppose that you know the spectrum of the channel, real part, imaginary part of eigenvalue Z alpha. Then using this constraint, you immediately arrive at the following constraint for the real part of the spectrum of arbitrary quantum channel. Well, if the channel is unital, this is a theorem, because for the unital semigroups, we prove this result. In particular, for the qubit channel, this result can be translated into this simple constraint. And actually, this constraint reproducing well-known result, which was found more than 20 years ago by Alguet and Fujiwara for the Pauli channels. Pauli channels are maps of this form, where sigmas are Pauli matrices and P alpha probability distribution. So the problem they pose was the following. Suppose you are given the spectrum of the channel. What are the constraints for the, well, you are given the spectrum of map of this form. What are the constraints for the spectrum which guarantees that this map is completely positive and trace preserving? And they found the conditions. These are conditions. And because for map like that, the spectrum is real, this condition is equivalent to Z1, right? To Z1, which follows from this constraint. So this is one application of our result. And the second is related to the problem of Markovianity of the channel. So let me discuss only the unital case for which we have a proof, but we believe that this result is universal. So suppose you are given a unital quantum channel phi. The question is it possible to find a Lindbladian L such that phi can be represented in this form, right? Actually, it was proved by Michael Wolf and collaborators that this problem is NP-hard, right? But we found necessary condition for that, and this condition follows from this constraint. Suppose, suppose that I know the my problem is to find L. Or to answer the question, is it possible to find L like that, right? So this is a spectrum of L, right? Real part and imaginary part. And this is a spectrum of the channel, because this is exponential of Lindbladian. So I compute the determinant. This is nothing but I have to multiply all eigenvalues of the channel, right? And now I use this constraint. And I immediately found that the determinant is upper bounded by this quantity for any alpha. So this immediately implies the following constraint, that any eigenvalue of quantum channel, absolute value of eigenvalue, is upper bounded by 1, but this is trivial because it follows from Frobenius-Perron theorem. But what is new is that apart from this outer disk of radius 1, you have also an inner disk of this radius, right? So instead of just single Frobenius-Perron disk of radius 1, you have a kind of Frobenius-Perron ring, right, with outer radius 1 and inner radius, which of course depends on the channel. example for the qubit channel. For the qubit channel, this set of constraints gives very simple result, right? And actually, this result was found recently independently by Davalos and collaborators and Zbyszek Puchała, Karol and others in this paper. Okay, so let me conclude. So it was proved that for any qubit Lindbladian, the following constraint for relaxation rate is always satisfied. And we conjecture that this constraint can be generalized for arbitrary d-dimensional system. And we were able to show that this is indeed true for physical generators corresponding to the well-known family of so-called Davis generators defined in terms of weak coupling limit approximation. It's well supported by numerical analysis. And using this, we were able to find new constraints for the spectra of channels and also necessary condition for Markovianity of arbitrary quantum channel. More details you can find in these two papers. Thank you very much.
Are there any questions? Okay, Maciek.
Very beautiful results, very impressive. The question that I have maybe goes back to qubit. It's the following thing. There is a possibility, normally you derive master equation by coupling to the quantum reservoir, but
yes,
you can also derive master equation by coupling to classical stochastic noise.
Exactly.
Okay? Now, my question is, has somebody looked into kind of decomposition of the Lindbladian into a part which is intrinsically quantum and which can be modeled by classical? I mean, in the case of your inequality for the qubit channel, the first one, of course, it is saturated by quantum spontaneous emission rate when the rate of the phase is 2 times, well, I don't remember, we were T1, T2 relation and so on. And all the access noise, so to say, usually can be modeled classically. So maybe this is the way also to attack these more general things.
Well, well, this is, of course, very good point. As far as I understand, you can model only unital channels, right? Unital evolutions, right? So for that we have a proof, right? But no, I understand the comment.
I'd like to have decomposition, that there is a classical part,
I see.
quantum part, and this is impressive.
I see.
Because then it's the most general.
I see.
Rafał?
So, what channel saturates the bound?
Very good point. Of course, you know the qubit channel, double commutator with sigma z, right? So now generalize it for arbitrary dimension. You replace sigma z by arbitrary Hermitian, and you have a double commutator with a Hermitian operator. And if you are careful about the spectrum of this Hermitian operator, you saturate the bound.
Suppose you have a Lindbladian that satisfies the detailed balance condition.
Yes.
Will it satisfy this inequality?
Yes.
Okay.
Good point, yes.
Okay, Professor Życzkowski.
A simple comment. Thanks for mentioning our papers. The last co-author of the paper, Puchała et al., is Łukasz Turski, related to the center. Thank you.
Thank you.
Are there any other questions? So maybe I would have one
Yes.
naive question. What about positivity of these maps? I mean, can you give some constraints on gammas for which the spots are not completely positive?
Yes, good point. Yes, for positivity, the constraint is very simple, just positivity of gammas, right? This is trivial. But of course, you may ask what a constraint for K positivity. Okay. And for that, we have another conjecture. You replace D by K.
Okay. It's tight, no? I guess. I mean, you have examples for which this conjecture.
Yes, we have.
Okay.
Yes.
Okay, let's thank Darek again for the nice talk. And I guess we go for lunch now. Do you have any announcement, Krzysiek? Okay, so well, let's go for lunch, and we meet again at 3.
Panu przekażę mikrofon. To chodzi o to, żeby te osoby online też wszystko słyszały. Musimy do mikrofonu mówić. Nie wiem, gdzie mówię.
Tu może.
On jest włączony. Teraz jest włączony.
Nic nie będę mógł zepsuć, jak go będę tylko trzymał.
Tak. Teoretycznie. Zawsze można. Nie ma takiej rzeczy, której nie dałoby się zrobić.
Patrzą na to, no jest dobrze, jest. Czasami każą te odsunąć additional data, kiedy zaszczepione i tak dalej. No, ale jak ja przyjeżdżałem, to mi kazali pokazać. Tak, tak. Ale czytali? Raz mi czytali w Warszawie. Ale chodzi o to, że samo odczytanie tego produktu jest bardzo łatwe, jak się na aplikację chodzi. No tak. I oni mają, co, no mogą mieć, na przykład mnie nawet w Warszawie nie płacą wtedy, a w Paryżu popatrzył na to Kraus. Zajrzałem do Pani pierwszy dzień obowiązywania. Pani przewodnicząca mnie spojrzała jak na głupiego. To ja jej pokazuję. Ciśnię na jaka szczepionka i naprawdę tak. Jest, to jej potem pokazała. Nie wiedziałem, co to jest. Ja się nie plastykuję. Ale zauważył Pan, że jak się otworzy ten kod w obywatelu, to najpierw jest zaciemniona dana słowa. Trzeba kliknąć w odpowiednim miejscu, żeby się było czytać.
Good afternoon. It's my pleasure to be a chairman for this afternoon session. And before I will let the true heroes of this afternoon, Professor Napiórkowski and Professor Załuska-Kotur and Professor Maria Ekiel-Jeżewska to speak, let me make some historical comment. Exactly 101 years ago, if we will have our conference on a proper year, that will be exactly 100 years ago, there was a meeting of a mathematical society of Göttingen conveyed by David Hilbert, on which among the speakers was a certain emanator who was not speaking on what you may think about it, but she was speaking on elementary divisor and general ideal theory. But that conference was somehow a predecessor of our meeting, for most of the talks on that conference were about physics. There was, and particularly for our today afternoon, one of the speakers was a student of Hendrik van der Waals, who was talking about the explanation of natural laws using a statistical mechanics basis. And the other talk was by a person who had very complicated names, I'm not going to read it, the epistemological basis of a special and general relativity. So we followed the steps of the nice and rather famous predecessors. And the first, our session is about the statistical physics, and the first speaker is our dear friend and colleague from Institute of Theoretical Physics at Warsaw University, Professor Marek Napiórkowski, who will be talking about the wetting transitions on soft substrates. And we decided that we are not going to do the experiments. I have a bottle of water with me, but Marek, the floor is yours.
Thank you, Łukasz. So let me begin. Let me begin with my warmest congratulations to the founders of Center for Theoretical Physics, for the members of this center, for really creating something of extraordinary high scientific level. So it's always for me a great pleasure to be with you and give a talk. So actually I add 4 exclamation marks, one for each decade. There should be maybe 41 exclamation marks, but so to say, to simplify the notation, I put 4 of them. So the subject of this talk is wetting transitions. And wetting transitions is a particular type of surface phase transitions. So I will talk about particular type of surface phase transitions. So you know, when you consider a statistical mechanical system, let's say a fluid, which is enclosed in a container with volume V and surface area of the walls A, and then you calculate the free energy. Let it be the grand canonical free energy, but that is not important, so to say. So among thermodynamic parameters, it also depends on the volume and on the surface area A. And then in the limit of large systems, you can really extract 2 important contributions to this thermodynamic potential, namely the bulk and the surface contribution. And the bulk contribution, by its definition, is proportional to the volume of the system, and the surface contribution is proportional to the area of the system. Okay. So what I will talk about today, I will concentrate on the surface contribution to the grand canonical potential for a particular system. You know, when we learn about phase transitions during our studies, we usually concentrate on the bulk properties, bulk phase diagram, etc., etc. In other words, we concentrate on the, I'm sorry, oh Jesus. We concentrate on the non-analyticities of this bulk free energy density, right? But the surface free energy density, this omega sub s, is also running, so to say, its own singular life, right? So, for example, the bulk phase diagram can be read off by looking at non-analyticities of this bulk function, bulk densities, and the surface non-analyticities are read off from this part. They are independent, so to say. So the bulk does not depend on the surface at all. However, this singular life of surface free energy density is running with the background of the singular bulk life. Okay. So my first encounter with the bulk properties was 50 years ago. So here is a photograph of my student's book. It's not very precise, but you can read off here a lecture by Dr. Łukasz Turski, and it's physics of condensed phase. And Łukasz was mostly talking about phase transitions, so to say. So I started to soak with phase transitions 50 years ago. Well, not at all. So, and you see, I was a diligent student, so yeah. Okay, and then you see, next year I had a seminar. I participated in a seminar run by Professor Białnicki-Birula and Dr. Jarosław Piasecki, and that was the seminar on renormalization. That's how it was called, but there was a big part about phase transitions and then renormalization in statistical physics. You know, that was the time when Kenneth Wilson was writing his seminal papers on renormalization, 71, 72. Yeah. So I'm, so to say, soaked with phase transitions, and I will tell you today about the wetting transitions on soft substrates. And this is based on a work we recently did together with two of my colleagues from Stuttgart, Lothar Schimmele and Siegfried Dietrich. So before I start talking about the wetting of soft substrates, let me mention briefly the ideas of wetting of inert substrates, because it's good somehow to prepare the background for all this. So the system which I will consider is a fluid, say semi-infinite fluid, in the presence of a substrate. Let it be also semi-infinite. Okay. So of course the properties of the fluid depend somehow on the way it interacts with the substrate. All right. But the substrate is inert. That means it influences the fluid, but fluid does not influence the substrate. Okay. And then it turns out that if you properly choose the thermodynamic state of the system, of the fluid, I mean, and also, so to say, tune the interactions within the fluid and the interactions between the substrate and the fluid, then a layer of liquid can form between the gas, which is far away, gaseous phase is far away from the substrate, and the substrate, okay? And we say that this layer of liquid wets the substrate. So this layer of liquid in this simplistic picture has a finite thickness. I call it L, and L depends on the thermodynamic state of the system. It's also parameterized by interactions in the system, but I put just temperature to signal the dependence on thermodynamic state of the fluid. Now, if we choose the thermodynamic state of the fluid in a proper way, and that means the following thing. We look at the bulk phase diagram, pressure versus temperature, and you see, this is the standard phase diagram in which you have three phases: gas, liquid, and solid. Let's concentrate on the area around the gas-liquid phase transition. So we are close to the gas-liquid coexistence line. This line, which terminates at the bulk critical point with critical temperature Tc. So once again, if we properly choose the interactions in the system, then it turns out that there is a particular temperature called the wetting temperature, which is below the critical temperature of the bulk system, such that if we approach this wetting temperature along the bulk liquid gas coexistence, slightly below it, so that far away from the substrate we have a gaseous phase. Then upon increasing temperature this way, towards TW, the thickness of this wetting layer increases. In theory, it increases infinitely. In practice, it's also a finite increase, but from, say, microscopic to macroscopic size. And this increase can be realized in two ways. There can be so-called first-order wetting. So here I plot the thickness of this wetting layer L as a function of temperature, and see I approach the TW, and there is a jump in the thickness from finite to infinite value. Here is infinity. And that is called the first-order wetting. Or it can take place in a continuous way. That means upon approaching the wetting temperature, the thickness increases to infinity continuously. And that is called critical wetting. And whether we have in a given system wetting at all, and if yes, then whether it's first or second order, so to say, first order or critical, that depends on the interactions in the system. On interactions within the fluid, and on interactions between the substrate and the fluid. So you see, here is this figure where you have the bulk background, but on this bulk background, you have a prominent point which reflects the surface phase transition. Wetting. Well, how to discuss wetting theoretically? There are various ways, but one that means how to get a theory from which you can read off the thickness of the wetting layer and its dependence on the thermodynamic state of the system and on the interactions. So there are various ways. For example, one way is to go to mesoscopic description, in which the only relevant degree of freedom is the thickness of this wetting layer. Okay, so if you forget about the motion of fluid particles, etc., you just concentrate on a single degree of freedom, that is the thickness of this interface. That means position of the liquid-gas interface. So one way is, say, to start with the density functional theory for an inhomogeneous fluid next to a substrate, which is a microscopic theory. Tomasz Maciążek was talking a little bit about that, but in a quantum, so to say, scenario, I'm discussing condensed matter, so everything depends on temperature, etc. And then what you do, you integrate out all the degrees of freedom which are consistent with the constraint of a prescribed thickness of this wetting layer. And then from what you get, you extract the surface contribution to this functional you are dealing with, and this surface contribution depends on the thickness of the wetting layer, right? It's not a function, it's not a free energy, it's a functional. And then it turns out that this surface free energy has this standard form. So first of all, it's proportional to the surface area of the substrate, right? Then there are three terms. There is a sigma SL, that is the surface tension coefficient between the substrate and the liquid, SL, if it were alone. Then there is a second contribution, which is the surface coefficient of the liquid gas, right? This interface, as if it were alone. And then there is a so-called effective interface potential, which describes the interaction of this interface with this interface, right? And then the equilibrium, it depends on L, of course. And then the equilibrium thickness of L is the one which minimizes this effective interface potential. So to say, in this approach, the whole thing is to find the effective interface potential and analyze its properties. So before I continue, let me tell you what is the typical scenario for this critical wetting. So critical wetting takes place when T approaches TW from below. We move along the bulk liquid gas coexistence line. And here is the behavior of this effective interface potential as a function of L. And please keep in mind that the minimum is the equilibrium position. That is the thing observed experimentally. So we see here are two minima, I would say, one at a finite value of L and one at infinity where the derivative is 0. And you see, if I increase the temperature, this potential behaves this way. So we see this finite minimum moves to the right in a continuous way. The potential becomes more and more shallow. And so to say, finally, the last picture of my motion picture is this. You see, the only minimum is the one at infinity. So in a continuous way, we obtain the infinite thickness of the wetting layer. In the first order wetting case, the behavior of this potential omega of L is different. It displays a minimum, a maximum, and then goes to 0 at infinity. And now if I increase the temperature towards the wetting temperature of first order transition, the potential behaves like that. So basically the minimum and the maximum don't move, only the depth and the height vary. And finally, if T is equal to TW, then the value at this finite, the value of omega at this finite L value and the value at infinity, which is 0, become identical, and that is the first order transition. Okay. So this is the mechanism. All right, so after this introduction, I can start talking about the wetting of soft substrates, because my question basically is, what is the influence of the softness of the substrate on the type of wetting transition? Okay, does it modify or not? What does it do? I would also like to tell you that if you look at experimental data, then most of the experiments show first order wetting transitions. They are, so to say, ubiquitous among wetting transitions. There are few papers on continuous wetting, critical wetting, but most of the transitions observed experimentally are first order. Okay, so now wetting of soft substrates. So again, I have a fluid. I mean, the scenario is the same. I have a fluid and a soft substrate. Now, the state of the fluid is described by its density, rho of R, and the state of the soft substrates is described by the displacement field, U of R. And the substrate is characterized, as in theory of elasticity, by two Lamé coefficients, lambda and nu. All right. So now the substrate is soft. That means it complies to the state of the fluid, right? It reacts to the changes going on within the fluid. All right, how to describe the system? I describe it within the functional theory, but now the functional theory depends on two fields, on the density, rho, and it depends on the displacement field, u. And there are three contributions to this functional. One comes from the fluid, one just itself. One comes from the substrate, the elastic substrate. And the third term is the interaction between these two subsystems. So the fluid density function for the fluid, which depends on its density exclusively, is written in the spirit of van der Waals, Hendrik van der Waals. So what is the idea? I mean, the idea of van der Waals was to split the interaction between the fluid particles into short-range repulsion and long-range attraction. And this potential W of R that is the part of the fluid particle interaction which describes the long-range attraction. So it's a negative thing and describes long-range attraction. The short-range repulsion is encoded here in the free energy of this short-range reference system. I will not specify the form of this function, but I would say it's known. Since this is a grand canonical potential, there is a term in which chemical potential multiplies the number of particles, fluid particles. And finally, let me stress again that this is van der Waals' description of the system in which we neglect fluctuations in the system. So what should sit here instead of the product of two fluid densities, we should have a two-density distribution function, which includes correlations. What we do, we neglect correlations, replace this two particle density by product of two one-particle densities, and that is van der Waals theory. Now, the substrate, that is something which I follow Professor Duszyński's statements, older generation would know. That is the theory of elasticity, standard, in which this functional is a functional of the strain tensor. Strain tensor is roughly the gradient of the displacement field. And it's a linear theory of elasticity, which means that the functional is a bilinear thing. So there is a term quadratic in the trace of the strain tensor. I stick to Einstein notation, the Einstein convention. And here is a term in which we have a product of two strain tensors summed over repeating indices. Okay, so this is the substrate contribution. And finally, there is an interaction between the two subsystems. Namely, again, in the spirit of mean field, we take the fluid substrate particle of the fluid, particle of the substrate interaction potential, which we multiply by the density of the fluid and the density of the substrate, and we integrate over the subsystems. Now, the density of the substrate, the density of the elastic body, is related in this linear theory of elasticity to the displacement field via this formula. So it's 1 minus the divergence of the displacement field, and rho 0 is a constant which describes the density of the substrate in the absence of any elasticity for inert substrate, I would say. All right, now what one does in the statistical physics business, one looks at the minimum of this functional. That means I have to minimize with respect to the density and with respect to the displacement field, and this gives me two equations, one scalar, one vector, for the equilibrium values of these fields. So I don't want to bother you with the details of this formulae, but maybe you look here. You see, these equations are coupled equations. So the upper equation, which, so to say, can be considered as an equation for the density, depends on the displacement field, and the lower equation, which is, so to say, the standard equation in theory of elasticity, that means equation for the displacement field, depends also on the fluid density, right? By the way, this equation I learned on a conference, it's called Navier-Lamé equation, the Navier from Navier-Stokes. And this is describes the state of the elastic substrate in the presence of bulk forces due to the fluid. Okay, so fluid modifies substrate, substrate modifies fluid, and all right. What do? We integrate out the elastic degrees of freedom. We try to get rid of U, so U equilibrium, so to say. And then if we assume additionally translational invariance in directions parallel to the substrate, then we are dealing not with the original potentials W of R and V of R, but their form integrated over the spatial dimension. So we get something which depends only on variable Z perpendicular to the substrate, and we get the equation which is the essence of this discussion. Namely, here is the equation for the equilibrium density. You see, I have written it in a way which tells you what is the effect of elasticity of the substrate. Because if we neglect those red terms, we would get just the standard equation which we obtain in the case of inert substrate. So what we get in the case of elastic substrate, after integrating out this elastic degrees of freedom, we get equation which has the same structure, except that here the density of the substrate is replaced by term 1 plus P over gamma. I will tell you in a moment, well, this gamma is sum of Lamé coefficients, lambda plus 2 nu. And what is even more important is that here, in addition to the direct interaction between the fluid particles, we have term which describes indirect interaction between the fluid particles. Namely, fluid particle interacts with the substrate, perturbs it, it gets distorted. This elastic distortion spread out through the substrate, and then the substrate interacts with the fluid particle. So we have a term bilinear in this fluid substrate interaction. Okay. But otherwise, the structure of this equation is well known for people working in theory of wetting. The modification which comes is this extra term, so to say, and this extra term, but this is essential. And by the way, you see, if you go with gamma to infinity, that means if your substrate becomes more and more hard, inert, then those terms disappear, of course. So what I will do now, I will consider the case of long-range forces. Namely, I will assume that the fluid-fluid interaction, this attractive long-range part, decays for large distances as 1 over r to power 6 van der Waals interactions, and the same for the substrate-fluid interaction, again 1 over r to power 6. And then I can do what I did for the equilibrium case, exactly on the level of functional. So I can obtain the functional for the surface contribution to the free energy in the soft substrate case, which has basically the same form as in the inert substrate case, except now that this effective functions, the effective potentials are different. One is omega tilde, the other is omega. Now, again, what is the relation of these two? Again, this soft substrate effective interface potential can be written as equal to the inert case plus a modification, and this modification is bilinear in this fluid substrate interactions. So here is a formula, details are not important. And here, for those who are interested, is the form of this effective interface potential in the inert case. You see it's a balance between the fluid substrate interaction and fluid-fluid interaction, so to say, weighted by the densities. All right. And these functions T are again functions of W as a function of integral over V. So if we assume that the thickness of the wetting layer is large enough, then we can make the expansion in powers of 1 over L. And large thickness means large compared to the bulk correlation length in the fluid, precisely in the liquid phase. Then we can say that these coefficients, omega tilde I, are related to coefficients omega I, so soft case is related to inert case, and the corrections are due to the softness of the substrate and are inversely proportional to 1 over gamma. Okay, now what are the conclusions? Namely, I call them soft substrate wetting versus inert substrate wetting. Again, I will consider two cases, critical wetting of inert substrate and first order wetting of inert substrate. So if inert substrate undergoes critical wetting at TW, and that takes place when this coefficient omega 2 is negative and becomes 0 at TW, while omega 3 is positive, then if the soft substrate is not too soft, I will not specify what I mean because that requires formulae, but too soft, is not too soft, then we again observe soft substrate critical wetting. So inert substrate critical wetting goes into soft substrate critical wetting, however, with a different wetting temperature. The wetting temperature goes down. And here is a formula for this change. We calculated this change for a particular system. Propanol, which is an alcohol, on silicon gel, which is a soft thing. And then we estimated for a particular choice of the materials, this relative change can be up to order of 20%. So it's substantial for this material. And then finally, when we have no soft substrate critical wetting, that is the case when the inert substrate critical wetting, when the inner substrate critical wetting turns first order due to elasticity, okay, due to softness. And that is the case when the soft substrate is really soft. Okay, so the softness induces the change from critical to first order. And finally, what happens if the inner substrate undergoes first order wetting? Then you can check that it is not possible that the first order wetting of inner substrate becomes critical in the soft case. Okay, no change in this direction. Okay, so in other words, my conclusion is, and that is a conclusion which is in line with the experimental observations, that soft substrates promote first order wetting transitions. Thank you very much.
Well, thank you very much. We have a time for one question or two short questions. Okay, Marish. Just a second. Wait for a microphone.
I would like to know how this picture would be modified if the fluid moves. Yeah, let's say there is a wind.
In which case?
The fluid moves.
If the fluid moves. I can't tell. We didn't discuss dynamics.
But the point is that if the density of fluid changes, then it also moves. By continuity equation, it has
Łukasz, the density changes, but it's all equilibrium picture. There is no time in this business.
Yeah, but that was the question. That what when the fluid moves, the time is involved.
Yeah, but my answer is we didn't discuss dynamics.
Yeah, okay.
Yeah. No. Yeah. But you know, then there is also a problem with transition in non-equilibrium setting. I mean, it's a somewhat different story.
Professor Załuska.
Just curious, can we say that if we have hard substrate, really stiff, this transition is continuous?
Usually, from experimental experience, it's usually first order.
So they don't observe?
They do, but very seldom.
Okay.
Yeah.
All right, thank you very much. Let's thank the speaker again. And our next speaker is Professor Magdalena Załuska-Kotur from the Sister Institute of Physics of Polish Academy of Science. And she will be talking about the diffusion on the interface of a solid and how it influences all sorts, as she called those phenomena in her abstract creatures, which can be created on the surface of the solid. There is a problem with those complicated devices. I always wonder, we have such a beautiful smartphones and so forth, it's still such an ugly conference speakers.
Okay, thank you.
All right,
thank
everything
you.
Is okay. So, Professor Załuska-Kotur.
Can we do it more? I don't know, fit.
I will raise
my
hands when you have the 5 minutes.
Okay. Good evening, everybody. I'm really happy to be here to celebrate with the institute with which I was related to, I was linked to, since I was a PhD student of Łukasz Turski. And then all years of my work were also somehow related to cooperation with people from the institute. And as Mariusz Gajda told 2 days ago, I was always fascinated with seminars in this institute that were full of discussions and usually didn't end at the place, yeah. At the end when they were supposed to, because everybody had a lot of questions, and I like it very much, and that was really very nice. So congratulations with this anniversary, and today I wanted to say something about surfaces of crystal surfaces, and diffusion-induced transitions at these surfaces. This title is quite long, but I will explain what is going here. Yes? Like this? I should switch on. Okay. Yeah. So when crystal grow, it doesn't matter what shape it takes. It always or it happens at the surface. So it is surface that decides what will be the shape, the final shape of this crystal. And so this is crucial. I mean, what happens at the surface. And this is how usually we think about this crystal surface. So we know that there are some steps, and there will be more about these steps further on. There are some dislocations at the surface. There are some islands, and there are atoms that move along surface. And how we understand this surface grow is that these atoms, when they move along surface, they attach to places like this one, and in such a way, layer by layer, nowadays people create structures, crystal structures that they want to. Okay, so why we want to control surface? Why we want to control this crystal growth? It is there are two main purposes. One is that we want to grow very good structure, well-ordered crystal, and for that we have to know how to control conditions under which this crystal grows. Second reason is creation some specified structures at the surface, and such structures are here shown. For example, nanowires, like we see here, or some meandered structures, as is shown here. Because such patterns or such structures, surface structures, are needed further for some applications. I mean, we want to use them for some purposes. So, crystal surface dynamics, as we built it theoretically and as we understand how it goes on, is composed by several parts, several items, like there is some external particle flux that comes to the surface, and it makes that this process we study is not equilibrium one, because there is there is always some external particle flux that comes to this system, and it makes that this crystal grows. We have some adsorption and desorption at terraces, so at the surface of crystal. We have surface diffusion. We have adsorption at steps, so at the places like this one. And we have some additional conditions under which such dynamics happens. Okay. So again, crystals, as I will think of or tell you about them, is just layer by layer ordered in given places particles, and there is this surface which has steps there. And why it has steps? Because those are the best places to attach particles. So those are places where this crystal grows. So people, when they prepare such system, they really prepare it as they say, with some miscuts. So they cut this crystal at some angle in order to have steps. So if we think about them, we just think about such system. So we know that it consists on some steps at the surface, but of course I can think of it as a surface that is simply shaped like this. Okay, so what kind of surface patterns they observe? What kind of surface patterns they really work with? So this is regular surface, and this is real crystal. So this is those are all pictures taken from experiment. Those are meandered. This is meandered surface. It means that steps, I don't know whether you can see it, but steps go like that. So like meanders, like this. Those are, this kind of surfaces are bunched surface. So surface is ordered like this. And some islands or mounds, however you call them, but this is also kind of self-organized structure at the surface. Some holes in surfaces or caves. So those are structures that go down, not up, and nanowires. Nanowires are now for several years, I think, or even more, of large interest, and the most maybe active field in this area is now about quantum computation and some special states that are believed to be found in such so ordered structures. And of course the question now is how to control those states, how to manipulate them. For that reason we need to know more about nanowires, how they grow, how they can be prepared, and so on. Similarly, people think about about structures that are somehow prepared at the surface, not just like nanowires on top of the surface, but along bunches, and that's why bunches are also very important in all the studies. So again, how we can understand pattern formation or structure, formation of structures of surface, and we can run, for example, molecular dynamics simulation. We can prepare such crystal, put single atoms at the top of the surface and see what happens. And those are trajectories of these objects that you see at this plot. But it takes a lot of time. It is fascinating to see that they really walk at the surface like this, but you don't see any real attachment to the step. After some time, this crystal below changes a little. So here you can see some kinks. And you have one particle that eventually attached to step. The step is here, so this is periodic boundary condition. But you don't have this process, you don't have crystal growth. You can make something like Monte Carlo simulations, and we did a lot of them. And you get, you reproduce patterns like I showed you before, but still there is a need to have some simple model, to model that is controllable. So you can change some parameters and know that they control, the specific parameters control the process. So, people with whom I was collaborating in this subject were people who make theory, but a lot of experimental groups with whom I was discussing. I knew from them which problems are really important and how they see these surfaces and what they want to ask about. Okay, so we constructed a model that is a basis for study of crystal growth, and it consists of two steps. The model to simulate such situation, and first step is just Monte Carlo process of diffusion of adatom at the surface. So they diffuse, and okay, I will tell you what potential I assume for such diffusion, but in the simplest version, each jump is equally probable, and they just move independently over the surface. And the second step is not Monte Carlo simulation, but this is cellular automaton. So I have stiff rules for attachment of particle to the crystal. So there is some layer that represents crystal below. This is the stepped surface, and particles that are at step are included, became part of crystal. And this is stiff rule. It simply happens like that. So for computer, it is very fast process. Moreover, I can add some other rules that allow to create island at the surface. So if two particles, they were independent particles before this step, and after this step, they became an island. Of course, if I do this 2 steps consecutively, so one by one, I will be run of, and this is density, this should be density here, number of particles will decay and I will have no more of them, so I keep density of particles constant. So in third step, I add particles to this layer of diffusing objects. So I have system that is easy to manipulate, easy to run, to simulate, and to change parameters that are that describe the system. And now I want only convince you that all patterns you have seen before and many more, are a result of the shape of potential at the surface that is filled by diffusing particles. So if particles diffuse at the surface, they can feel, for example, such potential. It means that it is deeper, energy potential is deeper at steps. It's at the same height for all other steps at terrace, and all particles in this first step of evolution, of simulation, run in such potential. But I can, for example, add some force. In such situation, my potential will look like that, which means that particles are driven in one direction, and it affects dynamics of all system, and it affects the pattern that results from this process. Or the other way around. I can add some force in different direction. Or, what will be shown further, I can change potential at step, and this has its name. It is Schwebel barrier, because Schwebel describe mechanism of step bunching, of creating bunches at the step by such barrier at step, and it can be here, it can be below this step, which usually is called inverse barrier, and I want to show you also result of combining these two types of barriers when I study the system and try to find out what kind of patterns are result of such simple assumption. So I have one simple assumption. I add and I change these two barriers, this one and this one, and also I do something with this barrier below them, but usually I keep it in such a way that jump from here to here or from here to here is exactly of the same rate as this one. The only thing I change here is this three energy values. So this one, and this one, and probability of particle to jump over here or over here depends on the height of this barrier. So, when I assume inverse Schwebel barrier, I have such process. So I start with such profile, surface profile. This is from side, shown from side, and it when time goes on, 5 minutes, okay. When time goes on, it changes in this direction. So bunches are larger and larger, and there is whole story of the, I mean, study of how it changes, I mean, with time, how it scales, and you can also show how it looks like as a function of time. So time is changing here, and bunches are created. You can study some stability diagram, and now I can show you results of two-dimensional model. It works exactly like this I discussed before, and I have this Schwebel barrier, and I can show you what happens with the surface. So if you have such barrier, you have meanders. You have bunches with this inverse barrier. You have nanowires. If your potential is shaped like this, it is the only case when it is of slightly different shape as the one I showed you before. You have such structures if it is like this, such structures if it is like this. And interesting, I've seen such structures grown experimentally with this, exactly of the same, of this shape. So this is interesting that people really see such shapes at the surface. Nanowires again, but they are realized differently. And kind of pyramids, they are not seen here well, but it is something we've seen from at the beginning as an example. We can study, because we can easily change parameters of our model, so we can study kind of diagrams as a function of jump probabilities over one barrier and over other barrier. And again, we can compare now our simulated structures with structures that are experimental. So you have at top, you have experimental structures, and at the bottom are our modeled structure. This and like this. The only remark I want to add here is that why we need that. I mean, what for we really need such model. This is because from the other side, we know how to control, sometimes we know how to control this Schwebel barrier experimentally. It depends on the kind of gas that is above this crystal surface. Sometimes it depends on other parameters, temperature, for example. And if we know how to control it, and we know how this system behaves as a function of these barriers, then we can tell what kind of parameters we should put in the experiment in order to get specific pattern, specific ordered structure. Thank you very much.
We have time for 2 questions. Remarks, comments, Marek.
So when you model the motion of the particles, right, on the surface,
yes,
do they interact among themselves or not?
They can, but in this simplest model, they don't.
They don't.
But of course, you can assume that they interact. But it, of course, you will put more parameters into this picture. So if you want to.
So your model is rather for low vapor pressures, right?
Yeah, but usually if you grow crystal, this pressure is rather low. So they.
Okay. Thank you.
Any other questions, comments? If not, then let's thank the speaker. And my pleasure is to introduce the last speaker for this session, Professor Maria Ekiel-Jeżewska from another sister institute of the Polish Academy of Science, Institute of Fundamental Engineering or Technological Research? Technological. When I was employed by the institute, there was a continuous debate whether this word EPPT, Instytut Podstawowych Problemów Techniki, should be translated as engineering science or not. Has those things work? Oh my goodness.
Dobrze? Czy pilot?
Does it work?
Nie mam kieszeni, to mam nadzieję. Dobrze.
Tylko duże przyciski naciskamy.
Dobrze.
Dobra. Okay.
Chyba tak, mam
So,
nadzieję.
technical problems have been solved, as was expected from somebody from Institute of Fundamental Technological Research. And Maria, the screen is yours.
So good afternoon, everybody. I would like to start from great thanks to the organizers for inviting me and giving me an opportunity to talk to you. And I would like to congratulate all the people working at the Center for Theoretical Physics. Congratulate their successful work and creating such a wonderful place. So I'm especially impressed by the development of astrophysics, because in 1980, when I started my employment in the center, my plan was to work on accretion disks and on the flow of matter and statistical physics of matter flowing onto the accretion disks. So the history of my research has changed a lot. So I worked on the relativistic Boltzmann equation in the context of previous possible applications to the accretion disks. But my PhD, made with under supervision of Professor Turski, was based on my contribution to joint work with Marek Dudzyński on very mathematical aspects of the relativistic Boltzmann equation. It means the existence, uniqueness, causality, and other properties of solutions to the relativistic Boltzmann equation. And I worked at the Center for Theoretical Physics for 11 years, and then I shifted for statistical physics of suspensions. And within the statistical physics of suspensions, I'm also interested on the dynamics of suspensions. I'm also very much interested in the dynamics of individual particles, let's say micron-sized particles, moving in viscous fluids, and especially moving under, let's say, under external forces, but also when they are immersed by the flow. And this dynamics is very appealing from the point of view for a theoretical physicist, because this is actually, when we have a collection of particles, this is like discovering Kepler laws in astronomy, but on the level of such a situation when we don't have the energy conservation, because these particles, when they interact with each other through the fluid, the energy is not conserved. And I would like to give you, and there is a lot of interest of applications of such dynamics of microparticles in fluids, because of some biological and medical applications, and also because of some new development of new, I would say, industrial technologies like microfluidics, for example. So what I would like to tell you, I would like to give you sort of spirit of this work. So I would like to present you one example, and this is the example of charged microparticles that are settling under gravity in a viscous fluid, and it turns out that they can form stable doublets, as illustrated here. Gravity is pointing down. And this is the result of my joint work with my PhD student, Christopher Trombley. And here is Christopher, and here there are listed papers and his PhD thesis, which has been recently submitted for review. So the basic observation comes from 1842, when Samuel Earnshaw formulated a theorem that there is no steady configuration of charged particles in vacuum that would be asymptotically stable for perturbations. And when we look at dynamics of particles settling in a viscous fluid, usually stationary configurations are not stable. And these are some examples. For example, when we have regular polygons, horizontal regular polygons of particles, they could be stable against perturbations, against some perturbations, if these polygons are less than 7. But if they are neutrally stable for blowing up and having configurations that are larger and smaller. And this is another example. The gravity is pointing down here, and there are two particles that are glued together and another one below them. And this system is stable against perturbations in this plane, but this is unstable against perturbations out of this plane. And the generic pattern of interaction between the microparticles in fluids, especially sedimenting under gravity, but not only, there is existence of many periodic orbits. Some of them are stable, and some of them are unstable, and very frequently these unstable periodic orbits, they originate sort of chaotic scattering of particles, let's say sedimenting under gravity. So the existence of periodic orbits is very closely associated with chaotic properties of the dynamics. So when we combine the Earnshaw statement about lack of stability and these observations from particles in the fluid where also this stability is absent, the question is what would happen if we combine these two? If we take charged particles and we put them into fluid. And it turns out that in this case, stable stationary configurations are possible, and moreover, they can have very large basins of attraction. So, and I would like to demonstrate you some examples. So, the simplest possible system is a system of two particles sedimenting under gravity. These are spherical particles, and they, in general, they have different radii, and the ratio of radii is denoted as gamma, and they in general have different masses. Reduced masses, it means masses corrected for buoyancy because they are in the fluid, and delta is the ratio of these masses. And there is also charge that is put on these particles, and the ratio of sort of electrostatic to gravitational forces on the second particle at the contact is called as the parameter beta. So, in addition, we have the influence of the fluid. So the influence of the fluid is described by this equation. So the point is that we are in a very viscous fluid where the effects of inertia can be neglected. So as the result, the external forces are exactly balanced by the hydrodynamic forces. And as the result, velocities of the particles, Ri is the position of the center of particle I, so the velocities of the particle are linear combinations of the forces exerted on both these particles. And these coefficients are called the mobility coefficients. And they are evaluated based on the Stokes equations for the fluid velocity and pressure. So what we worked with Chris, we worked on the simplest possible model, on the point force model. So in the point force model, we have just point forces that exert additional force on the fluid. And therefore, fluid velocity is given in terms of the green function acting on the forces and summed up with respect to both particles. And then the green tensor has a form of the Rosen tensor, and that is written here. So the idea of the point particles model is that the particle, the particle I is entrained by the fluid flow created by the particle I, and so this is this term, and plus a second term, this is a self term, and this is just a conventional Stokes velocity of a single particle. So although the particles are point-like, and this term does not depend on the size, but we need somehow to put to the point particle model by hand the radius of the particle to assign a certain Stokes velocity to this particle. And having such a system of equations, we can so these are the evolution equations for the relative position of the particles. So these are equations for the relative motion of the particles, and we ask, how about some stationary configurations? So first of all, I would like to tell you what is the situation without charge, in the absence of charge. So when we have identical particles, you can have a look at these equations, then every configuration is a stationary configuration, so this is a very boring dynamics, but this is neutrally stable because particles, if they are like that, they would move. If they are like this, they would also move without changing their relative position, but they are neutrally stable. So, so when we look at these equations, and we can have a look that there can be some stationary configurations for particles that are different from each other. And so what is here important is the Stokes velocity ratio here, and having the appropriate bounds on the ratio of radii and the ratio of masses, we can see that there will be some stationary configurations. And these stationary configurations are marked here by circles. So the dynamics is such that there are some saddle points, and there are other stationary states here, and there is a periodic motion. So particles, when they are very close to each other, they are trapped. But if one of these, so this is the graph here, there is particle 1, and this is the graph of relative trajectories of the particle 2 with respect to particle 1 which is at the center. So if particle 2 is far away, it will not be trapped by the particle 1, but it will just move along these lines. So although this is sort of mathematically interesting, but this is impractical to be able to detect a significant influence of such particles trapped with each other without charge. So the idea is that when we have this such a configuration of particles that are uncharged, and this is unstable against horizontal perturbations, then adding some charge, adding some electrostatic attraction, we can get this configuration to become stable. And so this is some algebra shown. So these are some dimensionless equations of motion, as you see. So this is a very simple, mathematically very simple system of two coupled ordinary differential equations of the first order that are nonlinear. And so then the behavior can be studied analytically and just using standard perturbation analysis. So we first analyzed vertical we analyzed vertical stationary states and checked for the stability. Stability is just described by such a set of equations for some alpha star. We assume that particles do not overlap here, and these functions g and f, they depend on all these three parameters here, on the ratio of particle radii, on charge, and on the ratio of the masses. So these are some examples that I showed on the first transparency. There are some examples of these stable doublets, vertical doublets of particles sedimenting in a fluid, and there are some parameters. So we can observe particles that the upper particle has a larger Stokes velocity or a smaller Stokes velocity. We can have solutions for very small, for very large distances, large differences between sizes of the particles, and also for sizes that are very comparable. And we can also have multiple stable stationary states for a single value, for a single set of values of the parameters. And also, what is interesting, that even for very small charge, we can have such stable stationary states, such stable stationary doublets. And these are some remarks. So you can see here the sort of phase space. So how so this dashed region corresponds to this range of parameters where these vertical stable stationary states can be found, and the intensity of gray means what should be the corresponding value of charge put on these particles. So as you can see, that there exists stable stationary states even with very large values of the distance between the two particles. And here I would like to give you some trajectories. So again, the smaller particle labeled 1 is in the center, and these are trajectories of the particle 2, the other particle, relative to this particle 1 that is in the center, the smaller one, just it's possible to choose. And these dots, these circles, they mean stationary states, and the black dot means the stable stationary state. So you can see clearly that a large number of trajectories end up on this stable stationary state, and we can say that let's say the cross section to trap one particle by the other is quite large in this case. So the units is the sum of the particle radii. So what we can also have, we can have two vertical stable stationary states. So then we again have a very large basin of attraction with a large cross section that is possible. And what is interesting that we can have also inclined stable stationary states. So such two particles for a certain choice of the parameters, they can form stable stationary states that are inclined with respect to gravity. And there could be also solutions with inclined and vertical stable stationary states, and again the same characteristic pattern is observed, that this is an attractive state with a large basin of attraction. And there could be also solutions for inverted for inverted Stokes velocity ratio for when the larger particles comes from below to be trapped again by the smaller particle. So, and finally, I would like to show you the phase diagram to somehow, if somebody would like to search in experiments for such doublets, then there is, this is the Stokes velocity, the ratio of Stokes velocities of the particles, and gamma is the ratio of particle radii. So these colored regions correspond to such values of the parameters for which stable stationary states can exist, for certain values of the interparticle distance, and for a certain value of charge. An analogous graph is shown also for the inclined vertical stationary states, and the color means how large can be the interparticle distance between these two particles in a stable doublet. So I would like then to conclude and to say that we have found charged sedimenting we have found that charged sedimenting particles, they can form doublets, and the basin of attraction of these states can be very large, and it can be observed for a wide range of the parameters. So of course the question is what could be possible applications. I don't know, but after this paper, the first paper was published, I get a visit of a person working on reduction of smog and pollution in the air, and he was very interested if such a mechanism of putting charge on these pollution particles and having another heavier particle that is also electrically charged, could it cause the pollution particles to fall down more efficiently. So it's open for applications, hopefully. Thank you very much. Thanks a lot.
We have ample time for discussion, questions. Professor Białnicki.
You said at some point, even for a very small charge, wonder what sets the scale here, because small means that small as compared to something. So
to the gravitational, in this case, it's to the gravitational force on the larger particle.
Okay, so you compare electrostatics to gravity. Okay, yeah. Thank you.
Any other questions, comments? Professor Duszyński.
I understand that the main equation of motion is that the velocity is proportional to the force. That's
yes, to the combination.
Yes. So how good are these equations? I mean, how good they reproduce the actual behavior of particles in?
It depends on the Reynolds number. If the Reynolds number is much smaller than 1, then it's a very good approximation. So in talking about microparticles in water, this is a very good approximation, because Reynolds number is very small for such systems.
So the results that you discussed were obtained numerically, I understand.
No,
analytically.
These are analytical equations, but of course the analysis was done. These trajectories were plotted numerically.
So can you reproduce this in an experiment? I mean, these configurations can be
I would be happy to do it. So I even just made some estimations, and I bought some Delrin and Teflon balls and tried to put them in a silicon oil, but then it turned out that this is very sensitive, and the density does not match what producers told. So So I will be happy to reproduce it, but it's very difficult. So we do some experiments. We have started to do some experiments, and what I learned from that it's really very difficult. So, and sometimes it gives results that are not that are difficult to be explained theoretically.
Well, any other question, comments? Well, if not, then let's thank the speaker again. Let's also thank all the speakers for this afternoon. And I understand that there is now the coffee break. So everybody is welcome to have a cup of coffee or whatever. Nie chciałbym wyłączyć tego w sposób.
Raz, dwa, trzy. Raz, dwa, trzy. Raz, dwa, trzy. Raz, dwa, trzy.
Hi, Joe. Hi, Joe. Can you hear me?
Hello.
Ah,
Can you hear me?
Yeah, yeah. Good to have you. Let me just
How
first
is the
switch.
volume?
Give me a sec.
See, I have to change my sound level. It's not very high.
Right. Don't worry. We have a dedicated personnel here, so I
Hang
can
on
hear
one
my
second.
echo.
I'm not doing well here for the sound. Let's just see if I can.
Okay.
How's that?
Okay. Hi, Joe. Good to see you. I mean, I don't know if you can see me, but I will try to wave for you to you.
Okay.
You now? Right. And Nick is also here. So you're talking to me and Nick for the moment because rest of the guys are on the coffee break. So.
Right, sorry, I have a problem because I can barely hear you. I have to try to do something about this. Just 1 minute. Hi, Joe. Let's see.
Hi, Joe.
Change my speakers.
Yeah, Joe is doing something with his volume. So we can hear you very well. So I guess maybe you have something with your computer.
Okay, I just turned up the volume. That works much better.
That works. Okay, so Nick says hi as well.
Okay.
Yeah, he was. So, and I also say hi, of course.
Okay, and say hi to Nick for me too.
Okay, he can hear you because you are audible. So we are here for the moment, two of us, because the rest of the people are on the coffee break. Okay. So we should reconvene quite soon. So thanks very much again for joining and for agreeing to be a speaker. Unfortunately, we're meeting in hybrid version, but everyone knows how things are. But I guess.
What does hybrid mean for you? How many people are there present?
Well, occasionally we have a couple of speakers that connects like you, but most of us are actually here on site. So we get the feeling of the back to the old normal nearly. So yeah, and we're going for the conference dinner tonight. So hopefully to do some gossip and usual stuff.
Yeah, there's about 40 people, I think, attending physically.
Yeah, so for the moment we have a very low rates in Poland, so it's quite relaxed. So yeah, so I will introduce you and Nick, and I'll just basically maybe take 2 minutes to explain physical cosmology session because we are the newest addition to the institute. So and then later of course we'll give you the floor.
Okay. Can we try sharing the screen?
Yes, we definitely should try that.
Okay, tell me when to go.
So
I just press share screen.
Yeah, give a sec because our technician is doing something else.
Okay, we're testing the microphone. That's kind of loud, isn't it? Okay, testing. 1, 2, 3, testing. Can you hear me, Joe?
I can hear you. Yes, Nick. Right.
Is it clear?
Can you hear me?
Yes, loud and clear.
Okay, great.
Okay, we would like to try the screen sharing now, if you don't mind. So you can start screen sharing, Joe, because you have the permissions. So you should work if you start the screen share. Okay.
So let me try to start my slideshow. How does that work?
Yeah, we see your slides. Very good.
Great. Okay. Good.
I can see you still have a Johns Hopkins affiliation.
I do indeed. That's right. Yeah.
Okay.
Very complicated. I have to go there soon, so I'm a little nervous. But anyway.
Good. So cosmology from the moon. That's very good. Good to start.
Yeah.
And then Nick later would tell us about the history of the lensing. Okay. So we'll connect very well, I think. Okay. We should start probably in 5 minutes. So. Should we start left with the... Czy zostawiamy czy zostawiamy 400-lecie?
To jakby ja jestem tutaj otwarty, jak Państwo uważacie.
No bo to idzie na kanał. W tej chwili.
W tej chwili idzie obraz z kamery, żeby zobaczyć, ale już nie wiem na swojego stolecie. A tutaj jakby, bo to są dwa oddzielne, więc pytanie po prostu, co Państwo wolą, żeby
So, okay, Joe, do you think you can manage within half an hour?
Oh yes, it should be fine. Right.
Very good. I mean, Nick will be very happy to hear that because he wants to borrow a few minutes here and there. But we manage anyways, don't worry.
Okay. I'll do what I can do. Just interrupt me if I am going on too much.
No, don't worry. We'll let you know. But yeah, we're more relaxed. It's the last session of the day, so it's only us standing between the participants and the conference dinner. So they have no choice. They need to stay with us to the bitter end. Because kidding.
Where are you having the conference dinner?
It's a cafe very close, basically like at the courtyard of the Warsaw University Observatory. So very close to the place where Bogdan Paczynski were, starting the whole story. And actually it's also very nicely located because it's at the edge of the botanical garden of the Warsaw University. So it's a different venue than we have a conference center. So we have to still get there. I think it's called Flora Cafe, which makes sense if it belongs to botanical garden.
And where is the meeting actually?
Our meeting is relatively close, 200 meters from our institute. So it's a bit southern centrish part of Warsaw. It's a conference center that belongs to I think monks order. They're called Barnabites, and we are looking for a place that we're just accommodating enough. And some of the places from academia that still have restrictions, and they are actually much more relaxed apparently. Well, we still have, of course, COVID rules and people wear masks, but we could hold the conference here, so it was very nice. Although I assure you that the venue has a certain taste of decoration. Okay, we slowly reconvening.
You mean that of the monastery or something? Is that what you mean?
Well, yeah, with plenty of, I would say, religious sculptures and paintings, but besides that, this is very modern conference center. Mm-hmm. Okay, so Joe, we will pause for a moment. People are filling the room, and then of course I will introduce the session, and then I will give the floor to you. So just a couple of minutes.
Sounds good. Hey, I see a familiar name there. Agnieszka, hello.
Hello, nice to see you. Hope I'm visible as well for a while.
Okay, it's 5 p.m. on my watch, so we'll be slowly starting the session. So hello, my name is Wojtek Helwing. I'm a faculty member of CFT, and it happens to be that I'm also I turned 41 years old just a couple of weeks ago, so I'm as old as the institute is, and this is amazing to be part of all of this. And of course, now we're gonna start physical cosmology session, but before I give the floor to our two distinguished speakers, I think I owe you a very short explanation. So, physical cosmology, this part of the conference and the session, is completely the newest addition to our institute. So that's why we don't have any alumni, and actually I'm very happy to have this on the program, and I think I really owe this to one person to mention this. So it's former director Lech Mankiewicz and his vision that you can accommodate quantum physicists, quantum information physicists, solid state, cold atom gas, astrophysicists, general relativists, and physical cosmologists in one place, that I have a pleasure to speak to you and participate in this conference, because it was his vision that physical cosmology should also find a place at the Center of Optical Physics. So as I said, we came I came 4 years ago to the Institute, and now we have a growing group together with Maciej Bilicki. I'm so happy to be interacting with all of you. So as I said, we don't have an alumni, but I also have a very pleasure to an honor to introduce to you two distinguished speakers today. So first is Joe Silk, and the second will be Nick Kaiser. And also so happens to be that both of them shared a very distinguished prize in our field, Gruber Prize, and they were both awarded in 2019. And if you modulo 2020, which was the lockdown, so I can present to you fresh awardees of the Gruber Prize, nearly straight from the prize award ceremony. So of course, without further ado, we'll start first with the Joe Silk, who actually have put a very tentative, interesting title, Cosmology from the Moon, 2 concepts to explore. So Joe, thank you very much for joining, and the floor is yours.
Thank you. Well, good afternoon, good evening, everybody. It's a real pleasure to be invited to help you celebrate the 40th +1 anniversary of the CTP. And I'm going to take a much longer view than the next 40 years, probably even long, maybe the next century even, to try to tell you where cosmology will be going, in my opinion. And so let's begin. A history of the universe. I think you can see my pointer. So this, many of you have seen before. On the right, we have the present universe, galaxies that formed, etc. As we go back in time, we explore before the galaxies, when the first bubbles of neutral gas were being ionized by the first stars. That's as far back as we have fairly robust probes at the moment. And then before then, there were some very rare things going on, maybe a few first stars, few first galaxies, very rare, hard to see. We try to push our way back, but at least there's light coming from there, and so we can see these things. When you go back further though, no stars, no black holes, nothing really, except the hydrogen clouds from which structure later formed. We call this the Dark Ages. And so I think it's the new frontier in astronomy and cosmology. And I'm going to tell you how we'll be exploring that. And so the red star shows you the epoch that we'll be exploring. And I'll show you how the reason for doing this is it's just not a glimpse of history, but it's more an amazing probe of the beginning of the universe, of inflation. And of the very small scale structure from which galaxies were built. And then even going beyond that, the second concept I'll be describing is a way of getting back to the first months of the universe even, by dissecting the cosmic microwave background radiation, the photons in that radiation. And you'll see that both of these experiments will have a very natural site, which will in fact be the moon. I'll show you it's a unique site from which one can do much of this futuristic cosmology. So let's begin. I just want to pay a tribute to Georges Lemaitre, because he really was the starting point for modern cosmology. And so what I'm going to show you is not greatly advertised, but it's really rather amazing. But Lemaitre, in this notebook of his in 1927, was able to predict, with Einstein's theory, thoroughly understood by him, the various possible models of cosmology, starting from the Big Bang, with deceleration or acceleration. And he, of course, added the famous constant to the equations, which I think some people view now is just another constant of nature. Others view it more perhaps as a puzzle for fundamental physics to address. But be that as it may, let me just show you one amazing prediction he made in one of his early papers on cosmology in 1933. So he realized that the energy of the vacuum would not be completely zero because of 0-point fluctuations of particles will be created and destroyed, pairs of particles, a la Heisenberg, on a time scale and length scale that's unmeasurable, but nevertheless, this would contribute to a quantum pressure. And he said then that the equation of state of this pressure was P equals minus rho c squared. Rho is density, P is pressure for the vacuum. So what is totally amazing to me is that this, what he calls is the meaning of a cosmic constant, is exactly what we think of today when we develop modern cosmical models, and we try to measure more precisely this ratio of pressure to density, if you like, that was just -1 in the simplest possible model. So what is completely amazing, I'll show you in a second, is that we haven't really got far beyond the metra in understanding any better what this dark energy, as he called it, is, this pressure of the vacuum. So the big advance in cosmology, of course, as many of you know, is that inflation was our major step forward since the early days of Lemaitre, Einstein, Lemaitre, etc., etc. 1981, inflation was really conjured up as an early phase transition that led to a dramatic expansion of the universe. And what we would, driven by a scalar field, the inflaton, and what we'd like to do very much is to understand this better. And in fact, while it's a wonderful theory that fits much of the data we have about the size of the universe, the flatness of the universe, we haven't really a very good recipe yet for testing this and for seeing, proof that it actually did occur. So one of the predictions, of course, is that there should be dark energy. That's what we have now, and that in some sense is what initially drove inflation too, long ago, this rapid expansion of the Lemaitre type expansion of the early universe. And we are no closer to treating this as more than a constant of nature than we were when inflation was developed. Likewise, dark matter, which is a natural prediction of inflation, because inflation produces a universe at the end of the day, is perfectly flat after the many, many decades of expansion. And again, we have no evidence of what this might be. So these are big question marks. So we can do a little better. What are we trying to do at the moment? Well, one marvelous prediction of inflation is that at the end there should have been produced naturally a gravity wave background, highly redshifted today, but visible as an imprint on the cosmic microwave background by a tensor mode, which we're trying very hard to distinguish. So that may or may not be there because we have so little information about what the inflaton was. But here are two more predictions. One is galaxy formation. Again, in our conventional model, it's cold dark matter. That's the dark matter. Inflation predicts lots of dark matter. And if it's cold, that means there are very small scales that gravitationally collapse into building blocks of larger scales. And these would lead to spectral distortions of the microwave background as they basically interact with the baryons and the photons, the dark matter. The combination inevitably gives you some heating of the universe, and that we're going to look for. We haven't found it yet. And then finally, inflation itself can be probed because generically it leads to non-Gaussianities in the initial fluctuations that can be seen as higher order correlations. So these latter two are totally new tests that so far we have not really even begun to develop realistic experiments for. And I'll try to develop for you where we might be going with these tests. Okay, first of all, dark matter. Very brief comments. It is everywhere in the universe. most likely it consists of some weakly interacting particles. We have some highly motivated searches because there are theories, especially one probably unsuccessful theory, a very compelling theory, grand unification, which predicts that dark matter should be some sort of Majorana-like particle which froze out in the early universe and have occasional annihilations today. So that's a wonderful thing to look for, and it's very much the dominant type of search. And there are other searches too. But the real problem is that in the parameter space of possible dark matter candidates, we have this huge range of unknown mass and unknown cross-section. And so far, we've just begun to search in tiny areas for the standard SUSY particle is a small part of parameter space, for sterile neutrinos another one, braxions another one, and so on. But all this parameter space is largely unknown. We've found nothing yet. So it does raise concerns about where we might be going in the future, because we've been looking desperately for 20 years and have found nothing. And so our philosophy is we look everywhere we can, and there have been wonderful underground experiments, astrophysical experiments using dwarf galaxies looking for dark matter, annihilations, and of course collider experiments looking for creation at high energy of occasional missing energy momentum jets, which would be indications of dark matter particles forming. So we've found nothing yet, and that is a problem. And one has to ask the question, where do we go next in cosmology? So that's all I want to tell you about dark matter. Big question mark. Dark energy, in fact, my conclusion is somewhat similar. In 2001, we had some major discovery, basically summarized here, Nobel Prizes awarded, very justly so, for the acceleration of the universe, basically a prediction of the W equals -1 in the equation of state that Lemaitre originally predicted. We still don't know why lambda is so small and why it's dominant now. These are interesting questions. Of course, it might just be a constant of nature, but the bottom line is the following, that the latest experiments, and this is the very latest, zero in on this W number in the equation of state, -1, and you can see in the early days, our precision was, plus or minus 10% or worse, but after 2 decades, we now have a few percent, 2-3%, and using the various different probes from the microwave background, from supernovae, from baryon acoustic oscillations. I don't have time to describe these in detail, it's sort of irrelevant really, but the point is that we're zeroing in at the 2% level, and W is always -1, with dark matter also unknown what it is. So that's frustrating, I would say. We don't know, as we build bigger and better cosmology experiments, whether we should be refining this number to ever more precisely look for deviation, or instead should we put our resources into something else? And that's a big question mark we have at the moment. Where do we go next? Modified gravity, maybe gravity is totally wrong. Well, I find when I look at this, I haven't dabbled much in the field myself, that when I was wonderful new physics, the motivation is much weaker than for Einstein gravity. And just to show you an analogy with my dark matter landscape, the landscape for dark energy, so for modified gravity. So here on the left, you have the size of whatever region you want to look at. On the horizontal line, the energy you're probing. And the point is that we've tested Einstein gravity in this yellow range, a very small range of this huge parameter space. And so that motivates us to look elsewhere in other parts of this enormous parameter space to try to see if, there's no reason to believe gravity may be the same everywhere. And this is the reason for looking beyond it. But as I say, I find the alternative to Einstein unattractive, uncompelling, I would say, at this point. And so let's move on then. So that maybe is not a direction we're going to go in. We see no future there. So maybe the major future for the next 10 years in cosmology to probe the beginning will come from the microwave background. So we've had wonderful results there from the Planck telescope, and we're now projecting 2 types of experiments in the near future. One is with a satellite, and the particular one that is going forward so far so well although not completely approved yet, is the LightBird satellite from Japan to do a space survey of the fluctuations post-Planck. At the same time, we'll have very powerful experiments installed, especially in Atacama region and also even more in the South Pole in the next few years, increasing our current sensitivity enormously, perhaps by an order of magnitude. So what is the aim of these experiments? Is to get a handle on the gravity waves as a probe inflation that are produced as inflation ends. So here the problem conceptually is the following, that what we do is we measure the tensor mode in the microwave background. We of course have to clean out all the many sources of foreground which might come from gravitational lensing by galaxies of background radiation sources. Also dust produces a micro background component, a foreground component that's polarized and can be confusing. But the ultimate problem is that even once you succeed in cleaning out all the foregrounds, you're left with the inflaton, the field that drives inflation. We have no idea what this is. If it is a modest fraction of the Planck mass, well, yes, you can get something measurable, but it could be much less. And so there's no guarantee that we'll get a future signal from polarization. So it will be wise, I think, to do other things too in cosmology as well. And let me then tell you now my first concept of where I want us to go in cosmology, or I can see us going in the future. So this is what I think is really one of the great new frontiers in the universe that's unexplored. And this is before the first stars. So imagine in this cartoon, you see the building blocks of a dark halo, many small clouds. We can estimate roughly what these sizes are because they need to be massive enough for gas to condense in them and cool and be the building blocks of galaxies. And so there are millions, precursors of every galaxy. And here is what you find, that when you study the power in terms of the scales that you're looking at in the microwave background, you get this famous power spectrum for the microwave background, but you run out of power at some point because of the damping of the fluctuations. And you have basically millions of modes to study. And you can't do any better than 1 over the square root of the modes. So that limits your precision in cosmology. If you look at large scale structure, we have wonderful new surveys coming along, space surveys using Euclid and ground-based ones using the Vera Rubin telescope, LSST survey, and that will give you, hundreds of millions of galaxies, independent modes maybe, if you analyze them carefully enough, and that pushes you further to smaller scales. But the ultimate is, if you can really get to the building blocks, the hydrogen clouds that were there before the first stars, before the first galaxies, then suddenly you can unleash trillions of modes, basically a million building blocks per galaxy. And this power, the inverse of the root of a trillion, gives you wonderful, wonderful precision. And so how do we go about unlocking this? Well, here's what you have to do. You have to build an interferometer that can look at really, really low frequencies. So as you look for the shadow of these clouds against the cosmic microwave background, that will happen before the first stars. But after that, you have stars, you have X-rays, many things from known baryons. So this is the history of the spin temperature of the hydrogen, a fine structure of the hydrogen atom that you look to probe neutral hydrogen with. And there is a magic window, roughly at redshift 50, where the spin temperature difference is maximal. It's of order tens of millikelvin. You see basically a shadow of gas in absorption against the microwave background because the gas is expanding slightly more rapidly and cooling more for a while. It couples earlier, couples later, but here's your magic sweet spot. So this is what you want to do. How do you go about doing this? Well, there's only one place to do this. It turns out that's the far side of the moon, because you have to go to 30 megahertz to probe this sweet spot of 50 at 21 centimeters. That means redshifting the 21 centimeter line to something like tens of meters of wavelength. So the good thing is that the moon may be full of rocks, But basically, you know, full of regolith, all sorts of weird things. But basically, you can lay down your interferometer. Here's a concept study from a decade ago, in which there was a mylar strip with printed dipoles on and a correlator somewhere, perhaps now it will be in orbit, to collate this signal. So what you do then, to summarize, you want to study redshift 50, wavelength of tens of meters, and you're looking at a resolution of something like the equivalent of one of these building block clouds, which turns out to be 100 times that of the resolution of the CMB so this is how you pick up all your modes, by going to much higher wave numbers. The optimal array size to get this resolution is something like 100 kilometers. You have to fill a 100-kilometer region of the far side of the moon. And let me emphasize it's the far side, because from the near side, we can see the Earth. And there's all this man-made noise that we don't want. That's a mess at low frequencies. Our cell phones, whatever, radar, all sorts of things. So the far side is quiet at the moment anyway, and that's where we can go. And to get the sensitivity, you need to fill this array, which the resolution forces you to have, with lots and lots of dipoles. That in principle is not such a complicated task. We understand the technology. We're busy building things like this on the Earth, not at such low frequencies, with hundreds of thousands of antennae of dipoles. When we're planning something for the moon, already with a pilot project, 128 antennae, be laid out by lunar rovers. This is under serious study at the moment, as an interferometer that will look back into the far side, from the far side of the moon to the early universe. So what is the problem? The problem is that at the end of the day, we're looking for this 10 millikelvin signal in what's a really, really bright sky foreground. So the sky comes from all these galaxies out there, and we can estimate roughly how bright the sky gets. It's been measured well at slightly higher frequencies, and it will be thousands of Kelvin. So you're looking for literally the needle in the haystack. Fortunately, there are clever ways to do this, because all the known foregrounds have structure in frequency and angular correlation structure, and you can try to use that to sort out this line signal, very unique to 21 centimeter redshifted to redshift 50. So it's going to be tough, and there are ways to do this by using your line of sight, for example, which effectively measures frequency along the line of sight, and in the sky you get angular correlations which measure physical length scales indirectly, and so you can use this sort of trick to carve out parameter space. So we know how to do this basically on the Earth, and the same principle in space could be done. And so here's the other part of the trick. It's all these radio sources that are a terrible problem. So how do you get rid of them? On the Earth, we know what to do to do radio mapping of faint sources, and look at diffuse backgrounds. We basically do source surveys. How do you do this on the moon? Well, you build a huge telescope on the far side of the moon. This is a scheme under intensive study also at the moment, to deploy an Arecibo-like telescope in a big crater on the far side. And this would have a suspended receiver at the focal point from the crater rims, and it would do direct imaging and help you to beat down this noise. So I don't think it's an impossible problem getting to where we want to go. And supposing you can do this, then here is the most amazing part of the science. You can basically, if you can get the sensitivity you need with these trillions of modes, you can look for the higher order corrections to the temperature fluctuations, which must have higher order corrections, basically driven by the physics of inflation. And so it turns out that in generic inflation models, there are correlations built in at the beginning. They're imprinted on the microwave background. They're imprinted on galaxy surveys. But these, we're just limited with the signal we can get at precision. But they're equally imprinted in the dark ages on the hydrogen clouds. And it turns out that you're looking for, it's a tiny, tiny effect. You can calculate what it is. And in generic inflation models, both single field and multi-field, there are estimates that this number that you're looking for, this correction should be of order 0.01. Remember, we're now looking for really tiny signals anyway, So getting there may not be totally impossible if you have the number of modes to get the precision you need. And so how do we go about doing this? Well, here's one indication that it won't be so difficult once we get to the moon. This shows you the 21 centimeter power spectrum that's predicted by standard inflation models. That's this red line here. And if you now boost the power by having such exotica as primordial black holes formerly, it's one of the popular models for dark matter, then you can have far more power because you need to make these black holes. And this pink area is the sensitivity range of this future lunar receiver. So interferometer and combined with interferometer. So the point is that what you would do first of all is look for the power on the small scales predicted by inflation and cold dark matter, and predicted even more if primordial black holes are a major part of our universe, which many people think they might be. And so that takes you part of the way, and then the next step is to then use this precision cosmology argument. Remember, I said just by counting the modes, you can get precisions of up to 1 trillion, and this means that you can suddenly do precision cosmology on the order of 1/√n, which gets you to equivalent FNLs, that is this parameter that measures the non-Gaussianly predicted by inflation of 0.01, and that's where you want to be. So the bottom line is you can test inflation, a robust inflation prediction with the dark ages, if you're adventurous enough to build these large telescopes on the far side of the moon. Okay, so that is my first concept. And now let me take you on to the second one briefly, because I think I'm running low on time. So here's another way to dig into a new frontier in the universe. The microwave background is this wonderful black body measured by the FIRAS instrument on board Kobe 30 years ago. We have not done better since. And these are, 400 sigma error bars, just amazingly precise black body. But at some level, smaller than these error bars, there should be distortions predicted originally by Suniev and Zeldovich. And this shows you the sort of distortions from a black body that you might expect. That is in terms of having frequency distortions, so a completely thermalized radiation field would be the black body, that's the red line. But if you in fact add injection of energy to the photons, and you shift photons from low to high frequencies, and you get these really intriguing distortions. And one of them in particular, which is just pure energy injection very early, where there are many scatterings, but after thermalization, so you don't remake black bodies, you can probe the universe back to 300,000, that's within months of the Big Bang. And so we'll suddenly learn about the universe really, really early. So to show you why this is so important and why it can be done, it's important because you can probe the many, many modes that make up the small scale structure that predict energy input into the universe from the small scale structure that makes up the galaxies. As with the 21 centimeter project, but now a totally different and complementary approach. How do you do this? Well, you build a Fourier transform interferometer, and you can't do this on the Earth, you need to go into space. And basically you compare the microwave background in this spectrometer with a reference, a very precise reference black body. That's all you need to do. You have to put this on a reasonable sized telescope, maybe much more than a meter or two. And you have to look at frequencies in the terahertz range to get these around the peak, below and above the peak of the black body radiation. So here's one scheme for doing this. One could do this as a free flyer in space. The budget would be a fortune, but it's not impossible. Going onto the moon, it's in a sense much simpler. You just dump a module into a dark and cold crater of this spectrometer. The sky is scanned as the sky moves, as the moon scans across the sky. The moon is fixed over the Earth, but the sky traverses. your orbit there as you look at the sky, and then you'll be able to improve on FIRS in principle by 5 orders of magnitude. Now, this experiment has been proposed several times to different agencies. One version was PIXI, proposed as a MIDEX to NASA, and it just was not powerful enough to get down to the limit of probing the small-scale structure of the galaxy distribution. But in principle, a bigger experiment could do this, and the moon might be one place to put this. And indeed, the ESA program recently has been studying what should we do for the next big, large project in space, ESA Voyager 2050. And here an example of the sensitivity one could achieve with such an experiment on either a free flyer on the moon. So this shows you the range of intensities you get. So first of all, here is the FIRS limit. The gray line is the total foreground. This is the obstacle you have to fight against to beat this down. And you can do this in various clever ways, and I have time to go into in principle. And if we look back at this, let me just talk about the red and the blue lines. But this mu energy input distortion from the very early universe is in quadrature shown in green, and here's the sensitivity you could expect to get from a future spectrometer on an off-suitable scale. And these wiggles are spectral lines, and that is totally amazing because you could, in principle, probe the line spectrum of hydrogen helium recombining in the early universe. To me, this is the most amazing part of the whole story because you can do what is bread and butter astronomy, recombination line astronomy in the early universe, and probe the universe back to a redshift of something like 10,000. And what is more, because these various transitions have timings associated with them, you can study all sorts of intriguing physics about setting limits of what the Earth might or might be doing in this early phase, testing dark energy, for example. So just to end very, very quickly, one can do much, much more than cosmology on the moon. So you can basically study exoplanets, look for them. And the amazing thing about the moon is that because gravity is low, you can build a much bigger telescope. There are no winds to blow your telescope over. So in principle, you could have a several 100-meter telescope on the moon. Someday we'll have this. It's not going to be soon. But with this, you can suddenly improve the yield of potential exoplanets with rocky cores in habitable zones around stars. And instead of getting the handful that we expect with future experiments planned in the next 20 or 30 years, we can suddenly get our yields up to many thousands. And that's probably what you need if you really want to search for signs of life. It's all in the numbers. And one more crazy idea for the moon, again, something that will happen someday, but I don't think immediately, is to mount in a cold shadowed crater many 5-meter mirror segments, have a focal plane suspended from the rims with your camera. And basically this hyperscope, if you can make the light coherent, and there are schemes for doing that, very futuristic schemes using quantum effects, but in principle, you could suddenly get images of exoplanets. Here's an example of the nearby system, but with this sort of resolution, imagine doing this for exoplanet astronomy. This would be totally amazing. You wouldn't need to arrange a flyby for a fraction of a second, as with one of the projects under discussion. You would have real ways of looking for interesting things. So I think that might be the future. So let me end. I think the point is that there are complementary concepts to probe small-scale power in cosmology, which is the key area where we're ignorant about what really is going on. And we need this to basically probe the beginning of the universe. So here on my summary slide shows you the power that Planck can have as I go to smaller and smaller length scales, where we are at the moment with the limits from FIRS of microwave background distortions and various lensing limits, which are even weaker on other scales. But if now we can suddenly unleash the dark ages, we can probe this whole new area from the lunar far side and really beat in on the small scales that Planck simply cannot see, but predicted by basic models. And that would be a wonderful way of testing structure but above all, eventually of testing primordial non-Gaussianity, the ultimate inflation prediction. And then finally, if you can do this in parallel, ESA Voyage 2050, one of its major projects for cosmology, is an L-class mission to probe recombination lines. And again, you'll be getting to, again, a whole new territory, redshift from 1,000 and 10 million. And the moon is a great place to do this too. Maybe not unique in this case, but it's a wonderful way to go to complementary experiments. So yeah, so that's my basic story. I think the space agencies are planning lunar space stations and villages and infrastructure in the next decade. There's enormous commercial interest in doing complementary things, which is a good thing for science because the big projects in science take very long lead times. Remember, we're talking about a collider, 100 TeV collider in 2050. The same timescale is true probably for science projects on the moon. And if we have all the infrastructure in place for commercial activities on the moon, which is one of the main goals of our space agencies now, long-term goals, and there's no reason why we couldn't be building telescopes. And the point is these telescopes can do incredible cosmology. It's stuff that you couldn't do on the Earth, you couldn't realistically do in space because the budget simply isn't there, and you'll be probing new frontiers, the dark ages, the universe before last scattering, that are totally new. Who knows what's going on there? And if you argue this stuff is absurdly expensive, well, let me remind you that the Hubble Space Telescope was only 5% of the International Space Station and Space Shuttle budget. So we're looking for maybe similar fractions in the future for the moon. And it's important now to lobby our space agencies to make sure that they have telescopes in mind as they project exploration of the moon with projects like Artemis and others that other countries are doing too. So thank you. That's the end of the story. And the bottom line also is, of course, that it's not just cosmology. There's far, far more to do with these lunar telescopes. I think the future is wonderful. It may be 2050 plus, but we've got to start planning now. Thank you.
Thank you very much, Joe. Thanks very much. Fortunately, we slightly out of time, so maybe we have a time for one or two short questions. I'm just going to remind you very simple rules. So if you want to ask a question, wait for the microphone to be delivered, and please introduce yourself because our speakers cannot see you. So do you have any questions for Joe? Yeah, we have one here.
So, Krzysztof Powolski, thank you for this nice talk. I'm not specialist in this field at all, but we have researchers working on theories which are predicted by Roger Penrose about conformal cyclic cosmology and Hawking points. So I'm interested, what's your opinion about that?
Well, of course, there we're talking about a really, really long time scale. I mean, I Googled whatever time, I've forgotten the units, but it's vast timescales. I find the predictions, well, the timescales are futuristic, and so are the predictions, in my opinion, because they involve assumptions about physics that are, I think, very, very hard to prove about, the decay of matter, for example. I think it's very nice to have a cyclic universe, but maybe there are other ways to do this that would not involve, to get through the singularity that would not involve such extreme new ideas. So I think we should be open to cyclic models. I think this particular one is incredibly hard to justify and to test.
Okay, thank you.
Thank you. Do we have another question? Last one over there. And Nick, if you could start setting up.
Thank you, Professor, for a very exciting talk. Mariana Haber. I would like to know your thoughts about prospects on detecting neutrino background with all of these exciting avenues in cosmology.
Well, I think that it's intriguing. There's an experiment called Ptolemy underway, which is intending to do this. I think it will need major funding and upgrading to get to anything feasible. But in principle, we can do it. it's a tritium type of and just designed to work at very low energies. So I think that's a wonderful prediction too. And that, fortunately, we can do that from the Earth. But it will take a lot of funding to build this detector. And I just don't know what timescale we can imagine doing this, but it's going to come sooner or later.
All right, thank you very much, Joe. And just a very short comment that your vision is very inspiring, and I think I will start repeating this to the fresh candidates for PhD students, because start doing cosmology now, maybe 20 years you won't win a ticket to the moon to service this experiments. So thank you very much, Joe. Thanks very much. And now we have another distinguished colleague, Nick Kaiser, who will tell us about the brief history of gravitational lensing in cosmology. And Nick is joining us in person here, so we can all enjoy this. And Nick, please go for it.
Thank you. Good. So thanks to the organizers for inviting me. It's a great pleasure to be here. It's been a fun meeting. So I thought it was a bit difficult to know what to present for a very diverse audience like this. So I decided to present a little history of gravitational lensing, which is an area that I've worked on from time to time over quite a while, since when I was a student. And it's gone from being a sort of small backwater of cosmology to now being one of the major advances that we're going to see in the next 10 years, with several billion-dollar scale missions. So how did we get there? It starts with this gentleman, Isaac Newton, who in his third volume of Optics put down 30 queries, about 40 queries. These weren't questions, these were statements that he was making. And the very first one in this box down here is that do not bodies act upon light at a distance and bend their rays? He's talking about gravitational lensing. Another one of his queries was the assertion that light is particles, and let's remind ourselves that it was already known what the speed of light was to 20% precision. So he had everything needed to do gravitational lensing, essentially as we know it now, within a factor 2. Now, the title's Gravitational Lensing in Cosmology, so you might ask, well, why didn't Newton finish it all off and do all of cosmology? Well, that might seem a little strange. You might ask, well, why would he even be thinking of that? Well, we don't need, that's difficult to know, but we know that he was thinking about it. We know that this from correspondence with Richard Bentley, and here's an example in the highlighted quote at the bottom, where he's directly talking about infinite distribution of masses. And it was pointed out after, cosmology was invented in 1922 by Friedman, the GR model of cosmology we use to this day to interpret observations. And as Milner McRae pointed out, Newton could have done essentially all of that, but he didn't. He couldn't get his head around the idea that the background would be dynamic. He thought it had to be static, and that was his stumbling block. But he was still able, the thing I like about this quote at the bottom is he's actually sort of skipping that and talking about the growth of structure in the universe. And it's what astrophysicists call the gene swindle. Anyway, so other people in the 18th century thought about light being affected by gravitating bodies, so we have black holes from Laplace. But light gravitational lensing takes a leap forward in the start of the 19th century with this strange character Henry Cavendish and Baron von Soldner, both of whom calculated that according to Newtonian theory, and this would be the picture, think of a mass passing a body, calculate how much it's being deflected, stick the speed of light in for the velocity of the body coming in, and you get the deflection of light. And the prediction is up there. It's about 0.8 arc seconds, which would be observable. And then we have to wait until the 20th century. You might wonder, why didn't something happen in the middle of the 19th century when a certain James Clerk Maxwell came up with a causal relativistic gauge field theory for something, but it wasn't gravity. It was electromagnetism. Why didn't he? It's really sensible to ask, why didn't he knock off gravity too and beat Einstein to it? Well, he didn't, but the reason is interesting, but I don't have time for it. So 1911, Einstein comes up with the idea, what he calls his happiest thought, the equivalence principle, and predicts light bending by the sun. And it's the same as the Newtonian prediction. People go out and try and measure it, actually 2 experiments, and both of them failed. They were weathered out. And then by 1915, he's finished the development of GR and realizes, in fact, the prediction for the light bending's different. It's a factor 2 larger. And as we know, Eddington went to test it and proved that he was right. So what happened between 1910 and 1915 when he went from the wrong answer to the right answer? So what he's doing with the equivalence principle, the idea that gravity and acceleration are equivalent, leads you to this, I can't see my pointer, it's there, this expression for the metric, right? He's done special relativity 1905, so he asked what is the metric in an accelerated frame according to special relativity, and time is warped there. And so, this means that if you and I are in a rocket, I'm in the tail, you're in at the back, then my clock runs faster than yours. Our clocks get out of synchrony. Well, why is that useful? Well, it predicts a lot of phenomenology of gravity. It predicts if particles follow extremal paths, it predicts that they move along parabolae. More interesting for us, is it predicts that there's a gravitational redshift, right? And from the gravitational redshift, we can calculate the deflection of light. Because if you imagine, look at the top thing, that's a beam of light coming in from the left that is going deeper in a potential well. The increase in the frequency means the waves get closer together. And that, because that's a function of height, that means this beam is going to get bent. And you can go from that to get Snell's law. Or you can think of the picture on the left, right, of invoking equivalence, that being in a gravitational field, it should be like being accelerated. And that's how he gets the wrong answer, right? No extra factor 2. The intervening years is developing the Einstein field equations, which you all know, right? And the way you can then use the gravitational curvature as you would use the Newtonian tidal field to calculate deflection. And now he gets a slightly different result in the Lorentz gauge for the metric. And there's now a warping of space as well. And when you calculate use the geodesic equation to calculate the deflection of light, you get twice the Newtonian answer. Right? And the way most of us think, a lot of cosmologists think about this, is we think about there being an effective refractive index. If you look at that metric up at the top, then null rays have 0 ds, and so they've got a coordinate speed of light. And so it's very much like the propagation of light in a medium with an inhomogeneous refractive index. There's a warning at the bottom. You've got to realize it's sort of analogous to that, but it's also completely not like that. Right? If you're in a swimming pool and I'm not, and I shine light into you, right, then you don't see any change in the frequency around you, but you measure its wavelengths order because you think you measure its speed to be different in the water. Right? In gravity, it's completely the opposite. So, you know, analogies are good but dangerous. And so what are the phenomena of lensing? There are three. One is the time delay, the Shapiro time delay. The second is effectively the derivative of that, gives you the deflection angle. So here's a nice cartoon of it. If we've got clusters and superclusters in the universe, then the light rays are going to take a sort of random walk. They're going to be slightly deflected each time they pass a cosmological structure. And when you calculate that, we know enough about the structure in the universe that that's dominated by large-scale structures, and it's about a 10 to the minus 3 effect. And then what's probably most interesting is taking another derivative, and you're getting the weak lensing phenomena, which is involves things, it gives you there's a 2x2 image distortion tensor whose trace gives you the magnification and change in flux densities, and the off-diagonal parts give you the distortion that you can measure of extended images. And this is harder because it's about a 1% effect on degree scales for sources at redshift 1. And something that'll be relevant in the last part of the talk is that this blows up as we go to small scales. For all we know, it actually diverges at small scales. George Ellis has a nice picture illustrating what your past light cone might look like with strong lensing going on. We'll come back to that later. So there's enormous numbers of applications of gravitational lensing in cosmology. I don't have time to talk about them. I'm going to focus on the weak lensing, and then the last part of the talk will be this bottom bullet. So I'll just skip over this extremely quickly. It was Fritz Zwicky in the 30s who first pointed out galaxies would make observable lenses, but it took until nearly 1980 for the first doubly imaged quasar to be measured. And the exciting thing there is that because quasars tend to be time varying, by looking at the time delay between the two images, you can get the Hubble constant, and that's become very interesting just recently. What weak lensing I'm going to talk about, I got into this in the mid-80s. Already 20 years before, Zeldovich had written a marvelous paper developing the ideas for this. But in the mid-80s, two things happened. People developed two techniques for probing dark matter with lensing. And one was this quasar-galaxy association. So quasars were at cosmological redshifts, except there were these strange associations with galaxies at lower redshifts. And the people who found these were considered to be cranks, right? And were just shunned by the mainstream. But they were right, but it wasn't a physical association. What was happening is that if you take a sample of just the bright quasars, you're more likely to see the ones that are behind galaxies. So the galaxy makes the background quasars brighter, they get into your sample. So you think there's a essential. It's complicated because actually for faint objects there's a diminution, but that's a technicality. So that gave people went and tried to measure it and got large results, which turned out to be wrong. That was a bit of confusion at the time. The next thing that happened, or a contemporary with this, Tony Tyson, who is the big leader of this, developed very deep imaging. And the first thing he did was so his technique was to look for the distortion of shapes of galaxies. So he takes quadrupole moments and calculates a sort of polarization from them, and does two things. He measures this on 20 fields around the sky and looks for a coherent, what we will call cosmic shear. He got a null result, and it's not that surprising. The other thing he did was looked at pairs of galaxies that were close together. He looks at pairs where one is bright and therefore nearby, and the other one is faint, and looks to see if the bright ones are causing a distortion of the images of the faint ones. And it's also measuring the mass around galaxies. And the prediction of these dashed lines, and the observation is a null result. So, very exciting, two results, they give completely conflicting results. But the big advance is when Tony turned his attention to clusters of galaxies, which are more powerful. And he looked at this is Abel 1689, and apologies for the quality of the images, this is old stuff. And he measures the distortion of the blue galaxies, the background galaxies, and from it finds this image at the bottom. And that is the image that launched 1,000 papers on this subject. This was a milestone. So a lot of words here, but really the impact of this can't be overestimated, because you're looking at a fairly strong lens, but the fact that you could see it there proved that there was a lot of signal to noise to be had on larger scales. So there was a lot of development to be done. Why were there these conflicting results? But let's just skip forward to a state-of-the-art measurement by a colleague of mine at ENS who did this analysis using the DES survey, and then where this will lead in the next golden decade of lensing. So I hope I've got enough time left to tell you now about a second bit of history of lensing, which is, gets a little bit more technical, but let me just make a little intermission. So this disappointing thing about lensing is that, all of us, most of us anyway, spent a long time studying general relativity, right? But if you want to do gravitational lensing, it's kind of disappointing that all you need to know is that it's twice what Newton would have got, which is kind of disappointing, right? That it's so simple. But that's actually wrong, right? And that may seem strange. So it's wrong in two ways. That you've got to be very careful. Well, it is dangerous and misleading to use your Newtonian intuition in general in lensing. One way it's wrong is if you calculate light bending in the lab. If I shine this measly laser pointer, this beam is getting bent, right? So should I use Einstein 1915 with the Lorentz gauge, which would predict a factor 2, or should I use Einstein 1910 to collect, which would say it's a factor 2 less? Right? Well, it turns out it's Newton's right. Right? So this very nice Lorentz gauge calculation gives the wrong answer. It's a gauge artifact. There's another thing, this is getting close to what I'm talking about next, is let's say imagine there's a well, an empty well, and you're at the bottom of it, right? If you work it out, you find there's a gravitational field in that well, which has a diverging, it's like a diverging lens, that if you were to take a bunch of pebbles and throw them straight up in the air, that gravitational field would cause those pebbles to diverge. So if it was correct to take Newton times 2, then light, that would act as a diverging lens for light as well. It doesn't. There's no effect for light. So now we're going to apply some of that stuff. So it's the same problem. So getting cosmological parameters, we use things like the Planck map, where you look at these ripples, and from that you can infer that the geometry of the spatial geometry of the universe is close to flat, for instance. But in doing that, you're assuming that we're looking at a surface whose distance from us is what it would be in a homogeneous universe. But we don't live in a homogeneous universe. So is there a bias caused by the fact that we're looking through a lumpy optical medium? Another pillar of cosmology is this Hubble diagram for supernovae. This is even more susceptible to possible biases in the distance. So I've highlighted there the distances we're talking about. In the first case, it's the angular diameter distance. It's an apparent distance. It depends on the cosmological parameters, and it says if you've got an object whose size you know, you divide by the distance to get the angular size. Similarly, luminosity distance, if you have a supernova of known luminosity, you divide by dl squared to get the observed flux density. And just to emphasize what we're trying to do here, everyone would agree that with structure, those become random functions of position on the sky. Things might be amplified or magnified or demagnified. The question is there a systematic bias? Because if there is, you'll get the wrong cosmological parameters. So again, this is a bit of a historical story because it goes back nearly 60 years to this marvelous paper by Zeldovich, where, to cut a long story short, he says things will look fainter in a lumpy universe than in a homogeneous universe. 1 year later, almost the same time, Feynman gave a talk on this. He didn't write it up, but Jim Gunn did in '67 and reached the same conclusion. Ron Kantowski did Swiss cheese models to calculate this, and Charles Dyer added a cosmological constant and actually produced a plot that observers could use to figure out, how big is the effect for, how much do I need to correct my observations for this effect. So all of these people agreed that lumpiness makes things look fainter, except Weinberg produces a paper in '76 where he says there's no effect at all, with a very elegant argument just using conservation of photons. So the argument goes like this. You say, imagine a source at the center of the universe, and imagine the sphere around it on which there are the observers who see that source to have redshift 1, let's say. Doesn't matter what the number is. Some of them will see it magnified, some will see it demagnified, but if photons are conserved, then on average, the flux density they measure has to be unbiased. So he's pulled the rug out completely, and that you might think is the end of the story, as, argumentum ad verecundium. He's a very distinguished person who gets most things right. Well, it's not the end of the story. So Peter Schneider, working with Jürgen Ehlers, comes along with a focusing theorem which says, in fact, that general relativity tells us that looking at things through a clumpy medium makes things look brighter. And there were actually two. I'll focus on the second. So this is a switchback in the story. Here are the suspects, and this is the final paragraph from their paper making this claim. So what are they doing? They're really doing General Relativity 101. All of you probably have had this course where you say the definition of curvature is what happens if you take a vector and parallel transport it around a loop. The curvature is defined to be its change, right? What you do is to do lensing, you say, let's take a photon 4 vector, parallel transport it and make a clone of it, and propagate those two photons forward through the lumpy matter, and then transport the cloned one back to the first one and compare them. If they're the same, then they've remained parallel. If there's a deflection, you've measured some sort of gravitational lensing effect, and then you what you can then do is consider a bundle of rays and take the area of the bundle of rays A, take its square root, and you find that it obeys this equation, and where that is the Ricci focusing term, which is the mean density plus possibly fluctuations, but they'll average out. But the key thing is there's an extra term here, which is the square is something, so it's positive. And that's the basis of the focusing theorem. And when you estimate, well, how big is that? It's like the mean squared shear. So it's this thing which gets large as you go to small angular scales. So as far as we know, it could be a large effect. Here, don't worry about the words. These are just some nice pictures of the people involved in this. And then Tom Kibble and Richard Lieu enter the game and point out something interesting which no one paid much attention to at the time, which is that they assume that Weinberg is right. That's usually a safe assumption. And say, well, yeah, Weinberg is saying that if you average the flux density, how bright things appear, averaged over sources, is unbiased by lensing. They pointed out that if you do something different, if instead of taking the sources, you look along directions, randomly chosen directions, say, and ask, how bright are the things I find there, and then average over directions, then it's not the flux density or mu that's unbiased, it's its inverse. So what on earth is going on here, and why is this interesting? The reason that there's some sort of difference between this different type of averaging is shown in this picture here. So imagine an observer surrounded by a shell with lensing stuff, with overdensities and underdensities, equally represented. The underdensities defocus the rays. The overdensities focus them. So you're going to find more sources behind the voids than behind the overdensities. And that introduces a bias. And that's essentially what they found out. And we're at 2005. The next step was 2014, when people started doing some rather complicated perturbation theory, second-order perturbation theory calculations of a cosmological nature. Luckily, they put two groups represented here, combined to produce a nice review paper, Reader's Digest version for people like me to understand what they're claiming. And this is essentially the argument, and they make the claim that they give a physical reason, that they say that they weren't aware actually of Weinberg's paper, but they're saying really that Weinberg made an error when he drew a sphere. Their point is it won't actually be a sphere, and they're right. So there's George Ellis, who used this diagram to attack Weinberg. It's not quite like that. I can explain to you offline, but it's more, the picture to have in mind is something like this, right? It's all about calculation of areas, and you've got to ask yourself, is the area of a dimpled sphere, first of all, is Weinberg wrong that he shouldn't have drawn a sphere, he should have drawn something like a golf ball, and how does the area get changed? So John Peacock and I decided, having seen all this and both being a bit confused, decided to figure out what was going on. And this is the setup. We say, what if there's some region, the grey sphere, with lumpiness? And we look at, for instance, I don't know, the microwave background, which is a surface of constant cosmological time when those photons came to us. Well, the light rays going through this perturbed region are not going to be straight. So that will affect the area of the last scattering sphere in two ways. In a certain amount of time, a straight line doesn't get us far. So that brings the surface closer to us, and that reduces its area. However, the area is no longer a sphere. It's got these corrugations on it, and that increases the area. And both of these, what we showed is both of these effects are of the same order, right? So we can just concentrate on the latter. How much does the corrugation change the area? And let's see if we can figure it out. How much, for instance, the area of that surface on the left, that swimming pool, is going to be slightly larger than the area that swimming pool surface would have if there were no waves, right? I see you all nodding. It's got to be, the change in the area is the fractional change has got to be quadratic in the amplitude, right? What can it be quadratic in? Well, the fractional change in the area is dimensionless. So the only thing that can enter is the angular tilt of the surface, right? If the RMS angular tilt is, I don't know, 10%, then there's going to be a 10 to the minus 2 change in the area. So that's all you need. If you accept that, then you come to the conclusion that because here the bending angle we already calculated to be 10 to the minus 3, then the error that Weinberg made is only 1 part in a million. So. And small print plus an equation for those of you who want proof we actually did some work. And then the second point we made is related to Kibble and Liu, is you've got to be careful what you average. Because if you use the wrong quantity, say you take the square root of the flux density, that's not going to be unbiased. Simple statistics because of this thing I tried to explain earlier. So these are the conclusions. The first part of the talk was a history of how we go from Newton via Einstein to the next golden decade with Euclid, LST, SST, and eventually SKA. And the second one is another problem that kicked around for now nearly 60, well, it was resolved after about 55 years of lots of smart people looking at the problem and coming to different conclusions. So thank you for your attention.
Thank you very much, Nick. Thanks very much. Do we have any question for Nick? Also, one over there, Nikolai. Please wait for the mic. And then Julius.
Hello, Mikołaj Korzyński here. Thank you for a very nice talk. I was very, I like a lot the second part of your talk about this controversy regarding the averaging over inhomogeneous structure. I wonder how these arguments are affected by the presence of caustics along the line of sight, because they do appear and they cause very significant changes of shear or other optical quantities.
Yeah, no, they're going to be seen. If I can go back. Whenever you have the strong lensing, you're going to have caustics. So, what happens here is if we turn this upside down and make the point P the source, then there are caustics here that if you move in space and cross from the region where you see one source into here where you now see two more sources, then you've crossed caustics. Right, so they're deeply related to this. So I'm glad you asked this. It's a very good question. So George's point is that this causes the surface area to be greatly increased because it's folded over on itself. But I believe that that's a red herring. That see, would that affect supernovae? Well, it would if you could resolve the multiple images. But in fact, you can't. So the splitting of the images is too small to be resolved. So all you observe is an aggregated flux density. So if you saw the micro images, the mean flux density would be decreased, as George argued. But in reality, it's not there. But thank you for raising that.
Julius?
It's almost the same question, but it's related to the fact that on this averaging argument, well, we have this some beams of light diverge, some beams of light converge, and on average we get some number. However, when we pass the caustic, then the converging beams suddenly become diverging. So then there is a sort of bias that every time we cross a caustic. And again, by George Ellis, he proposed a number of 10 to 22, something very incredible. So I don't know how, is this still, is this taken into account, or is this becomes irrelevant in the end?
The multiple imaging raises its head in this calculation in various places. But, you know, for the reason I said, if we're worried, it would be most important for the supernovae. And I honestly believe if you aggregate the flux densities, then you don't see that effect. There's one interesting thing that I just throw this out as it's relevant to this, is when you cross a caustic, you see two new images appear. Infinitely bright. They have opposite parity. They're mirror images of one of each other. And interestingly, in the Kibble and Liu argument, they had to do a little bit of fancy footwork. So their 1 over mu, mu being the magnification, includes the parity. So they count negative parity images as having a negative flux. So that adds, again, to the confusion. I think, though, in terms of, you know, we took to task the people doing these perturbation theory calculations. We think they've misunderstood what those result in. And for those calculations, the strong lensing is just not there. It's not part of the calculation. It's, you know, the effect of large-scale structure doesn't involve multiple images. Sorry to go so long.
All right, since we actually 20 minutes behind the schedule, so I think there's no more time for questions. Let's thank Nika and Joe again. And I don't know if you have any announcements regarding the conference dinner. And well, thank you for staying with us for the third day of the conference. And Krzysztof, do you have any announcement?
It's not announcements, just a reminder that we'll meet at 7:30 at Flora Cafe, Ujazdowski 4. Oh, thank you, we have seen the map. So, as I told you, there is a barrier in front of the entrance. Still, you can enter by car, but you have to wait a little bit until they will open, they raise the barrier.